So each speaker will be asked to give their permission. If they do not give the permission, then in that case, we will pause the recording for that session and then restart the recording from the next session onwards. Okay, so I will now hand over to Tanuja to get our session on healthcare started. We have a few more minutes, so we can take like a 3-4 minute break before we start, so that if there are last minute people who are joining in the last minute, then they can still attend. Our sessions formally start from 9:45. We can start a little bit ahead. That's fine as well. Okay, Tanuja, off to you.
Thank you, Amit. So we will wait for another 2 minutes maybe, and we will start the session at 9:40.
Sure, sure. I will stop sharing my screen.
I can share my slides already, so if there's any technical issues, we can figure this out in the meantime.
Yeah, that's a good idea.
Yeah,
This is working fine.
Slides look good. Yeah. So Florian, you've been with Remedio since when?
It's been almost 4 years now.
Oh, okay. Yeah, I mean, I have known Remedio for some time because Anand is my batchmate from my undergrad.
Oh,
So
okay.
yeah, so I know him pretty well.
So Florian, while we are waiting, are you okay to record this session?
Yeah, it's fine. It's fine. No problem.
So Amit, can you please start the recording?
The recording is already going on, so
Okay, cool.
so it will go on by default. If anybody has an issue, then we'll pause, stop the recording for the time.
Sounds great.
See, Tanuja, you see a record button, a red record button at the bottom, which means it's already recording. Do you see that?
I'm not able to see
I
the
see one on the top right.
Yeah, top
You can
right
see
is
on
for
the
on the
top.
presenters,
It is in
for
progress.
everybody, but for people, the host should have been able to see that, but that's fine. I'll be there anyway.
Cool. So maybe I think we can get started with the session.
Yeah.
Okay, should I go ahead?
So thank you, Amit, for the overview on today's symposium. And I'm excited to kick off the session on computing advances and AI in healthcare. A few housekeeping points. In this session, we would have 3 talks of 25 minutes each. So I'm requesting audience to type in their questions in the chat window during the talk. We shall take the questions at the end of each talk. With this, let's start with the first talk on deep learning for medical diagnosis from academia to real-world deployment. I would like to invite our first speaker, Florian Savoy. Florian is a computer vision and AI expert, and after bachelor's and master's of science at EPFL in Switzerland, he spent half a decade in research in Singapore, working on different computer vision applications. He then left academia to co-found Medios Technologies, an AI ophthalmology startup, which later merged with Remedio. So Remedio designs portable, affordable, and easy to use ophthalmic equipment with integrated AI. Florian is now VP of AI and Data Science at Remedio and leads AI development team. He is working on various AI solutions for the detection of retinal diseases such as diabetic retinopathy, glaucoma, and retinopathy for prematurity. So welcome, Florian, and the stage is yours.
Okay, can you hear me well? All good?
Yes, all good.
Okay. All right, thanks a lot for the invitation to speak today. So my talk, deep learning for medical diagnosis. I will split this in three main parts. In the first third of the talk, I will explain a bit more about Remedio's approach to AI. So the first third will be very company specific, and then I will take a step back and talk a bit more about the history and future of AI in healthcare in more general terms, since I'm the first to speak in this healthcare session, so that will give a bit more background. And then I will finish the last third of the presentation by giving what I feel are key considerations for building AI in the medical space to actually make it work on the ground, and what are the aspects you usually overlooking if you do that in an academic perspective, and what are the crucial points that you need to take care of. So let me start with Remedio's approach to AI. So we need to start with the hardware, and Remedio has been around since more than 10 years now, and is in the business of developing high quality, portable, and affordable retinal cameras. So what you have on the left is a standard retinal camera. That's a device that is in ophthalmology practice, and that's capturing images of the back of the eye, your retina. So you need to go through the pupil, which is a small dark portion of the eye, go through that and go capture the back of the eye. And that's where you can diagnose a few diseases that can lead to blindness. The issues we see with those cameras, they are all too expensive and bulky for a generalist screening context. They are kept in the ophthalmology practice. And what we realize is that you don't want to go to an ophthalmologist just for the purpose of being screened, of assessing whether you have a condition or not. So we're really trying to build technology that brings screening towards the primary care setting, towards screening camps, even in areas where it's a bit more challenging. You might not even have electricity and so on, but people are going blind because of those diseases. So on the hardware front was the flagship product of Remedio is called the Fundus on Phone, which is what you see on the right. That's the same equipment as on the left. It has the same purpose, except that it's being shrink into a device that is built as an attachment to a smartphone. And it's been clinically validated against high-end cameras to also be able to detect the diseases that you see in those images. But it's far more portable and far more affordable. So what you have on the right is a device that can be bought and by every GP, by every screening center, but the missing piece that AI is solving is making sense of the images, because you need expert eye expertise, ophthalmology expertise to make sense of those images. So that's where we bring AI into the picture. So I co-founded Medios Technology, a startup 4 years ago with my co-founder is the only computer scientist in a family of diabetes doctors. And that's where the problem statement came from. So in the hospital, they can screen for almost any complication of diabetes except diabetic retinopathy, which is the one affecting vision. And they had to send all their diabetes patients to an ophthalmologist, to an eye specialist, just for the purpose of screening. And what they realize is that most people, their vision is fine. They don't want to have the trouble to go for a second appointment. It's really hard to get an appointment over there because ophthalmologists are way too many people to see. So that's where we saw the potential of using AI as a triaging tool in here. When my co-founder pitched that idea, I went into the literature and I realized that academia had solved this problem with a great accuracy, but no one has brought that to market. So we tried to ask ourselves, like, what is going wrong and what do we need to do differently? And we realized that academia was using a very high quality curated data set that were gathered with the camera on the left. Perfect, clear images. You can really see all the details in there. But then if you go into real world condition, if you go in screening camps, you have more than not so pretty images you see on the right here. So you don't necessarily see all the tiny details. You might not be able to stage the progression of the disease accurately, but that's more than good enough to detect whether there's something wrong with the eye and whether the person needs to go see a specialist. So we really frame our AI solution as a triaging tool that says, yes, no, you need to go to a specialist to get referred afterwards. And we also realize that most of the AI solutions use like the traditional deployment model, which is a server somewhere and an API call to get the diagnosis back. But when we speak with doctors where they see their patients, people who operate screening camps, internet is a major issue. So that's why we start thinking, how can we do that better? And the fact that the remedial camera is built as an attachment of a smartphone really gives us all the tools to deploy the AI offline directly onto the device. And we have an AI algorithm that runs in seconds and integrates very well in the clinical workflow. So the healthcare worker captured the images, few clicks of a button later, the specialist knows whether the patient in front of them have an issue and need to be forwarded to a specialist despite not having any ophthalmology knowledge themselves. This is a bit of bragging. Google went in that field as well, but from the very academic perspective, and then went to India to deploy their model and realized that their model was failing of the kind of images that were captured in that context with somewhat lower quality camera, and that's really telling us that the need is not in a very accurate algorithm that works on great images, but really good enough with the kind of images you get when you go in the field and capture images of the patients. So those are the three main diseases we detect through our AI. The first one is diabetic retinopathy, which has affected 103 million people globally. So if you have diabetes for 5 years, it can start affecting your eyes. And the tricky issue with this disease is you don't notice anything until one day you get blind. And if you go blind, then it's too late for treatment. So you really need to start treating the disease before you start noticing anything. That's why screening is very important. So diabetic retinopathy is our first AI. It just got HSA approved in Singapore. We're in the process of getting approvals in Europe, and it's being commercialized in India already since a few years now. We are starting to commercialize in India our glaucoma solution that is also one of the major diseases with 100 million people affected globally. And we're in the final stages for age-related macular degeneration, which is a disease that affects 196 million people globally. So with this, you have a camera and an AI system that is able to screen for all the major complications of the eye and all the major complications that can lead to blindness in a single device that can be used by any healthcare worker. And I think that's one of the key strengths of AI at the moment. It really allows specific medical expertise to be given in a format that is making it much less accessible to the masses, to people who don't necessarily have access to specialist care. So that's really the company motto: anywhere, anytime, by anyone, anywhere. Screening camp, optometrist, general ophthalmologist, remote camps without internet or even electricity. The device is battery operated, and then you just need an operator of healthcare worker which has been trained for a few hours to operate the device, nothing else. And one last slide to say that AI can go beyond detecting diseases. So the trickiest part of using a retinal camera is actually finding the right time to capture an image, because you need to go through the pupil of the patient and then focus on the back of the retina. You need to be at the right working distance and click at the right time. What we've built, so it's lagging a bit, is an AI algorithm that analyzes all the frames one after the other in the live view and detects when is the right time to click the actual image. And that has significantly improved the ease of use of the device. So when you think about AI, it's not only about diagnosis, but it can really be an integral part of the device itself. So this concludes the first part of my my talk. I will talk a bit more about the history and future of AI in healthcare. Right now, taking a step back, this is a bit of the history of artificial intelligence, a big summary. That's actually a very pretty old field, much older than people think. The buzzword artificial intelligence is all over the place right now, but it actually dates for quite a few decades already. The name AI, artificial intelligence, was coined in the Dartmouth workshop in 1956. That's what is considered the birthplace of AI. And then you have different phases, and in between you have what is called an AI winter. So you have phases where there's a lot of excitement, there's a lot of funding, and researchers then tend to overpromise a bit, and then you realize that the technology is not as doesn't go as far as promised, and then funding drops, and you have what are called these AI winters. So the first big phase was between 1956 and 1974, which is called the symbolic AI phase. So here, now when we speak about AI, it's all about data and getting the computer to find how to solve a problem without hard coding the rules ourselves, but just letting the computer figure out how to solve a problem by just presenting a vast data set to the computer. That's how it's done right now. Before that, it was more a rule-based approach and using logic and some smart way to search into large data sets to get some advances. So the next slide presents a few applications in the medical field from each of those phases. 1974 to 1980 is the first AI winter. Then in the 80s, it was more the era of the expert systems. So AI was all about finding ways to encode and organize the knowledge of a very specific domain of expertise and organize this into logical rules. So it was primarily decision trees. And how do we find ways to help the expertise of, for example, in the field of ophthalmology, if there's decisions to be made, how do we hard code this into logical rules? And that's what was called expert systems. Then came the second AI winter, and from 1993 to 2011, it was really thinking about intelligent agents. So you have a small program that perceives the word and you try to reason with that in mind and trying to have some kind of intelligence in that intelligent agent. That's when the AI started relying on the field of probabilities and decision theories more and more. You had the first neural networks coming into the picture. That was the time when you had the computer beat human at chess for the first time, the first driving vehicles. And from 2011 to now, we are now in the deep learning and big data era. Neural networks, which is the biggest way to the biggest technology behind right now, is actually a pretty old technology. But what brought is really to focus right now is the major advances on the hardware front in computational power that allowed neural network to really scale and solve much more challenging tasks that weren't solvable before. So a few examples in the medical space. The first ever AI algorithm, so-called AI at that time, was MYCIN, which was a program that lists potential bacterial pathogens and recommends antibiotic treatment based on the patient. And that was just a decision tree with a knowledge base of about 600 rules, and the doctor was asked a series of questions until the program could find the answer. In 1986, you had the Explain, which is also a decision support system, and the doctor was inputting a list of symptoms, and then the program was looking into a database to try to find a differential diagnosis matching those symptoms. And then 2007, Watson's from IBM, neural language processing and various searching databases to try match a diagnosis to the data with several applications in healthcare being investigated. what's important to note about the first two applications, I don't know about the third one, but those were purely academic exercises, because at that time you wouldn't see a single computer in a doctor's practice. And it's only with the digitization of healthcare that those kind of systems went into the picture. So the current applications of AI in healthcare right now, it's the biggest, by far the biggest focus is on disease diagnosis. So that's also what we're doing at Remedio, with deep learning playing a more and more important role, but you have also SVM support vector machines and decision trees, working with images, also 3D scans, sometimes text data as well. There's applications in a lot of domains, ophthalmology, of course, cardiovascular, risk stratification, dermatology, gastroenterology, and so on. Radiology is also a big one. There are also more and more applications in telemedicine, where here more and more remote monitoring of the patient through sensors. AI is able to track changes that are less noticeable to humans, and advances in natural language processing also give us chatbot therapies, primarily on the psychology front, where instead of talking to a psychologist, you can have some kind of chatbot interactions. There's some applications coming in electronic health records, where natural language processing can also help make reports more succinct, finding similar cases in a database of patient cases, despite the wording used by the doctor being slightly different from one case to the other. And there's also quite some work being done in drug interactions, where in order to find them, you need to scrape through a whole lot of literature. And NLP is really helping with that, because finding those interactions in the vast literature is, I would say, beyond human capability. What is the future? Where are we headed with AI in healthcare? There are four key directions here. The first one is what we're already working on, reducing missed or misdiagnosis. What I mean by misdiagnosis is the doctor being sometimes too tired, missing a tiny detail in an image, and that can lead to a misdiagnosis. So AI, clinical decision support systems, can be used to highlight some areas of the image that might be problematic, where the doctor who can get their attention. Misdiagnosis is more the case where the patient doesn't have the opportunity to be diagnosed because of lack of expertise, and AI is brought here as a triaging tool. There will be more and more self-management applications, where here we all have smartphones right now, and we will see more healthcare applications on the smartphone. For example, you have an issue with your skin, something you want to get checked, but you don't want to go all the way to see a doctor. You take a picture with your smartphone, the AI is giving you a diagnosis, and then you'll know whether you need to see a specialist or not based on that. A lot of work is also done in reducing the administrative burden. I think that's more of an issue in the West. The motto here is making healthcare human again. Doctors spend a lot of time just with bureaucracy, data entering, filing everything that needs to be filed for reimbursement, and natural language processing can help those aspects, causing doctor fatigue and also removing precious time the doctor spent with the patient. And of course, what we were really into at Remedio is healthcare democratization, bringing more and more specialist care into underserved population that lack the physical specialists. So I have 6 minutes left to talk a bit more about what are the key considerations for building AI in the medical space. So this is the traditional AI development. I want to insist on the fact that it's an agile process. So when you work in academic settings or maybe at university, you tend to have your project deliverable set in stone, your data set is set in stone. You don't really reconsider that, and the key is really to train the model and find the best possible accuracy. When you work in practice, you constantly reconsidering all the aspects here. So the project setup deliverables is, okay, you want to tackle a disease. what do you do? Do you detect all the stages of the disease? Do you have a binary classification on patients that need to be referred, patients that don't need to be referred? Where do you put the threshold? What makes sense from a clinical practice, but also what is possible with the data set you have? Then based on that, you get your data set, data collection, labeling. I have a slide about that later on. Then only the model training and tuning is somehow the easiest steps, because if you have your data right, model training would be fairly easy. If you get your data wrong, then you can spend a lot of time fine-tuning your model when the actual issue is in the data set. Then device integration, clinical validation of the end-to-end product, and finally model monitoring. Data set collection and labeling, that's, I would say, the main issue for data in healthcare. You need a robust ground truth to build AI algorithm, but you're not in the token AI problem where you're distinguishing cats and dogs in pictures and you know very well whether it's a cat or a dog in there. You're trying to detect a disease from which doctors might not even agree on what is the diagnosis in the image. And this disease is not a black and white thing where there's no disease and there's disease. It's a slow progression. So you really need to find what is the right segregation of your data and where you put your threshold. So there are several strategies you rely on here. Consensus gradings, you ask several doctors to read the same image. You take the consensus. If junior doctors you're using to label the data don't agree, you get a senior doctor involved. What we did in the case of glaucoma, where it's a disease where fundus images is just one modality. You have a lot more tests that can be done to detect the disease. So we're getting all these other tests to get a more reliable ground truth for our data. And another key aspect with data collection is that the data set should be unbiased and diverse. Multiple camera systems, multiple ethnicities in there. If you take a public data set that was gathered in California that is available on the web, and you try to build a model to solve screening issues in India, it's likely going to fail. You need to have your ethnicities right. And varying image quality, I've talked about that already, and really needs to be representative of the population and the context in which it is deployed. And of course, the data set needs to be large enough for model convergence. One of the big hurdles we also have in the medical space, rightly so, is the regulatory issues. So when started in that field 4 years ago, it wasn't near where it is right now. Luckily, this is moving ahead. The process of designing AI models is very different from traditional software engineering. So all the ISO processes and so on, some have to be adapted. And in the US, you have the first autonomous AI being approved by the FDA, which is the agency regulating medical devices and other healthcare related things, which was approved in 2018. That was one of our competitors, IDXDR, for diabetic retinopathy detection. You have now a white paper being released where the FDA is proposing some regulatory frameworks and guidelines on how do you update an AI model and have continuous training of the model while ensuring the accuracy is good enough for the medical device and there's no issues regarding performance, because you don't want to do a full-fledged FDA submission every time you update your model. So that's work in progress. And the FDA also put up a very good document called the Good Machine Learning Practice, which is basically an outline of a machine development workflow with all the different regulatory requirements you have at each of the different steps. In Europe, we're going through a big revamp of the entire medical device landscape regulation called the MDD to MDR. At the same time, the European Parliament is proposing a new Artificial Intelligence Act to regulate all the high-risk AI systems. So this goes beyond medical, but is also very applicable to the medical field. Some emphasis on data and data governance, transparency, human oversight, and robustness. And the key aspect of this is that it has an annex called Annex 4, which provides a very detailed and comprehensive checklist of all the technical documentation you need to do for an AI system. And it's really AI driven. So everything you need to document in terms of the data set, in terms of the training process is there. And that Annex 4 is really giving us a lot of clarity on what kind of documentation we need to put together in order to get an approval. So I would say this is a big step forward in terms of the regulatory. Clinical validations, there's two kinds of clinical validation. Internal validation is usually your test set that you set aside during training, where you make sure the model works. But in the medical field, you need to go much beyond this. You need to do external validations. You need to deploy your model inside the device. You go out in the field and you check prospectively how the whole system is working. And here there are guidelines as well, but that's the most critical part of it. And sometimes you have pretty bad surprise with your external validation and that's when you realize your internal validation, the test set and your training set were not that representative of the real world scenario. And sometimes even after the external validation, you need to go back to your model and make some adjustments that you didn't saw before. Implementation, last slide. There's currently two ways to implement an AI system in the field. The first one, which requires more higher regulatory burden, is to have an autonomous AI. So that's what we're trying to do at Remedio, where you have a healthcare worker that doesn't know much, anything about the field that the AI is working on, capturing the images, and then the AI is autonomously giving a diagnosis, and then the patient goes to a specialist care. The other approach is to use AI as a complement to a clinician, as a clinical decision support. So here you still have a human in the loop, you still have human oversight, but the AI helps the clinician. So the clinician can have the opinion of the AI. In neural networks, you have those things called activation maps, where it's highlighting which area of the image has triggered the diagnosis. And that can be also very helpful to the clinician to make sure he's not missing an important detail or so on. And I have a small video to conclude the talk. That's our glaucoma AI on action. So that's the capturing process running the AI, and then you have the report, the glaucoma report coming straight to the device. This is the image capturing process, where the auto capture AI detects the right time. Then you have the images being captured, and then you select the images for report generation. And then you have your AI running live on the device, and then in a few seconds you have a glaucoma diagnosis with a PDF report that can be exported. And that's it for my talk. I think we can move towards the Q&A session.
Thank you, Florian, for such an informative talk and specifically highlighting the approach and steps in deploying the AI healthcare system in real-world deployments beyond the research phase. So I think we have one question I can see on the chat right now. So this question is from Anusha. And the question is, what are some of the techniques used to reduce the size of models and make them deployable on the edge devices?
So I think there are a few ways around this. I think that's a consideration that needs to be done from the very beginning of the model training. So you will use architectures that are meant to be deployed on a mobile device. So those are your efficient net, mobile net, and those architectures that have been created for that purpose. And then the Apple ecosystem, we're using iPhones in our devices has CoreML, which is this Apple framework that allows you to convert the model into into a way that make it very efficient to run on the GPU of an iPhone. And at the end of the day, if you look at the most recent iPhones, the GPUs they have in there, sometimes it's as powerful as the GPU you can have on a computer, so you don't need that much model compression. I'd say to summarize the key considerations here is a lightweight model architecture from the beginning, and then use the tools given by Apple, the smartphone providers, to deploy your model in the most efficient way on the device.
Thank you. And we have one more question here. So the other question is, for research purpose, whether these medical images data is available publicly.
It all depends on the data set. There are some data sets that are made available publicly by some research groups for different diseases. For all the three diseases we are tackling, diabetic retinopathy, glaucoma, and AMD, you find some data sets online. For the other data sets we're gathering ourselves to build our AIs, those are not public. We have research agreements with some hospitals where we collaboration agreements, and the data sharing is governed by those agreements. They also go through ethics committee approvals by the hospitals. So for those, it's a bit trickier. But for all the diseases I mentioned, you find some data sets publicly available online.
Great. Thank you, Florian. Thank you for this amazing talk. And I think we will move to the second talk in this session now. I would like to invite our second speaker, Nipun Patra. Nipun is a principal researcher and my colleague at Microsoft Research in India. Currently, his research interests lie in the application of computing and AI for low-cost healthcare and in problems at the intersection of computer systems and deep learning. Prior to joining Microsoft Research, Nipun co-founded a startup in the personal video space. And before that, he spent 4 years at Google in search ads backend and web search infrastructure teams. Nipun received his BTech in Computer Science from IIT Delhi, Masters in Computer Science from Georgia Tech, and PhD in Computer Science from Stanford University. So over to you, Nipun. Nipun, you are still on mute.
Can you hear me?
Yes, we can hear you now.
Sorry, I'm having some technical trouble here. Just give me a second. Somehow I'm not able to see the WebEx interface in front of me.
So meanwhile, Florian, I think you are seeing some questions on the chat. So yeah, please feel free to respond to the chat. Yeah.
So Nipun, what are you seeing right now?
Yeah, I think I'm set now. Can you see my slide and see me?
Yeah, we can see your slide.
We can.
Great.
And Nipun, you're okay to record the talk?
Yes, I'm okay.
Yeah, cool. Thank you so much and take over.
Thank you, Tanuja. Good morning, everyone. I'm Nipun Quatra from Microsoft Research India, and today I'll be talking about our work on low-cost diagnostics, led by me and my fellow researcher, Mohit Jain. So yeah, although healthcare has seen many advances over the last century, in many regions around the world, healthcare is unfortunately still inaccessible to a large population. And there are a variety of reasons for that, including skewed doctor-to-patient ratio, unskilled to semi-skilled healthcare workers, long waiting and long commute times to see a doctor, which also results in loss of income for daily wage earners. In our group, we focus on the diagnostic aspect of healthcare, and the access to diagnostics is primarily impacted by three axes: the cost of the diagnostic devices, the portability of these devices, which determines their reachability to remote areas, and the skill required to use these devices. In our work, we aim to help democratize diagnosis by attacking all the three axes. Our vision is to develop a low-cost smartphone-based diagnostic tools actually with AI assistants in them to enable community health workers, teachers, primary clinicians, and even Swiggy and Zomato workers to perform preliminary screening with minimal training. With that vision in mind, over the past few years, we have been working towards developing a variety of diagnostic tools from keratoconus diagnosis, which is an eye disease, to lung disease detection. Let me quickly run over two of these projects and then I'll dive deeper into another two. First, we have been looking at the dry eye problem, a condition which causes low quality tear film. The tear film of the eye has a lipid layer on an oil layer on top of an aqueous layer. When the oil layer is thin, it breaks up quickly, leading to evaporation from the underlying aqueous layer. This in turn causes irritation and burning sensation of the eye, and it's commonly known as dry eye. To diagnose dry eye, we rely on the principle of white light interferometry. As you may have noticed, when oil is spilled over water, we see a rainbow of colors. Similarly, for a healthy eye, due to the nice oil layer or lipid layer over the watery eye, one sees this rainbow of colors after every blink. In the dry eye, however, the lipid layer is very thin, which leads to only gray colors, as you can see on the image on the video on the right. We use a two-phone setup, one for projecting the light and another phone for recording the video, followed by a video processing pipeline to estimate the lipid layer thickness. This gives us a quantitative measure of the eye dryness. Next, we proposed a deep learning solution to classify crackle and wheeze sounds from chest auscultation data captured by digital stethoscope. We obtained state-of-the-art results on the largest public respiratory dataset at that time. Now I will dive a bit deeper into our work on automating retinoscopy. This work was done in very close collaboration with doctors from the Shankar Eye Hospital. For context, Shankar Eye Foundation is a network of 12 eye hospitals in India and among the world's largest community eye care providers. For example, they have performed over 2.3 million eye surgeries free for the underprivileged Indians. Okay, so as many of you may know, refractive error is the most common eye disorder, and it happens when the optical system of the eye is not able to focus the light properly on the retina. For example, as shown in the images, in normal vision, the eye focuses objects perfectly on the retina, while in the case of myopia or hyperopia, the focal point is either in front or behind the retina. Although refractive error is a very common problem and it may seem like a solved problem, it turns out that the condition goes undiagnosed for many people around the world. For example, according to a 2015 study, undiagnosed refractive error was responsible for vision impairment in around 128 million people worldwide. And the more startling stat is that out of the 36 million people blind worldwide, 20.6% were blind simply because of undiagnosed refractive error. That is, if they were given the right prescription glasses, they would come out of blindness. Okay, let's take a look at a few methods to diagnose refractive error. The gold standard and the most accurate method is the vision chart or the logmar chart. Many of you may have seen this already. This is a subjective method where the patient has to subjectively assess their vision. Although very accurate, the main drawback of this method is that it requires a lot of patient cooperation, and which many of you may have experienced is not always available. And this is especially a problem for young children who are not able to communicate. The second method is autorefractor. This is an objective method which does not require subjective assessment with the patient. And the biggest plus is that it is automatic. Although it requires very little cooperation from the patient, although it requires some cooperation, so it cannot be used for young children, very young children still. And other drawbacks include its cost and higher errors. The next method is retinoscopy. This is also an objective method like the autorefractor, and the biggest plus it has is that it requires minimal patient cooperation, and as such it can be even used for infants. It is much more accurate than autorefractor and actually can also be used to screen for other eye disorders such as cataract and keratoconus. In fact, at Shankara Hospital, anyone who comes for a consultation first goes through retinoscopy to screen for any other eye disorder. The biggest drawback of retinoscopy, however, is that it requires a lot of expertise to operate and is a time-consuming process. And retinoscopy is typically performed by optometrists, which is a 3-year bachelor's course in India. Now, if you look at the segment of young children, retinoscopy is the main recommended option by experts for refractive error diagnosis. And moreover, it is very important to screen young children for refractive errors, as undiagnosed refractive error can lead to a serious eye disorder known as amblyopia. Amblyopia, also known as lazy eye, occurs when one eye is weaker than the other eye. In such cases, what happens is that the brain will start seeing a blurred image from the weaker eye and a relatively sharper image from the better eye. And in many such cases, the brain can decide to start ignoring the blurred input and only rely on the sharper input. And if left untreated, it can lead to an irreversible and complete loss of vision from the weaker eye. Note that the treatment of lazy eye is quite simple if detected on times. First, the patient is prescribed the correcting eyeglasses, and then they are required to patch the stronger eye for a few hours a day so that the brain is forced to process the weaker eye. All this makes refraction error screening very important for young children. And thus, we believe that retinoscopy, which is the main tool for refraction error screening for young children, is a very important tool against preventable blindness. Now let's take a quick look at how retinoscopy is actually performed. Here is the image of the retinoscope on the left. It is a small handheld device with a light beam source on one side and a peephole to look from the other side. During the examination, the optometrist shines a beam of light from the retinoscope towards the patient's eye and observes what is called a retinal reflex. Let's take a look at a real retinoscopy video. The optometrist moves this retinoscope's beam over the eye, and when the beam enters the eye, it focuses on the retina and shines back to form this reflex. You can notice this reflex inside the pupil. I'll let you take a look at the reflex. This thing inside the pupil, this is called the reflex. And I'll skip a few details, but here is a high level of how retinoscopy works. It turns out that when the patient has a positive power, the reflex moves in the same direction as the beam. For example, here the beam is moving from right to left. So is the reflex. That's also moving from right to left. This is called with motion. And if the patient has a negative power, the reflex actually moves in the opposite direction. Like here, the beam moves from right to left, but the reflex is moving from left to right. And this is called against motion. And if the patient has zero power, we get what is called neutralization. In this, the reflex completely fills up the pupil when the beam passes over it. Let's have another look. It completely fills up the pupil when the beam passes over it. So what the optometrists do is as follows. They have this lens kit, as you can see on the image, and that has lenses of all powers. And they keep trying out different lenses from the lens kit until they achieve this neutralization we just saw. And the power of this neutralizing lens can then be used to determine the patient's refractive power. Of course, the optometrist cannot try all lenses as that will take forever. Thus, they need to judge from the observed reflex, the direction of the reflex, the speed of the reflex on what lens they think will lead to neutralization. This makes retinoscopy a very highly skilled and iterative process. And the chair time of an optometrist is about 10 minutes per patient. In fact, in most hospitals, including Shankara, first they get an autorefractor reading to get a good starting point, and then do retinoscopy so that they can reduce the precious chair time of the optometrist. Okay, as discussed earlier, for democratizing diagnosis, we look at these three axes: cost, portability, and skill. And at the cost and portability front, retinoscopy already fares reasonably okay. However, the biggest problem which we just saw is the skill requirement. And this is especially problematic due to a severe shortage of optometrists in many regions around the world. For example, in 2014, Sudan, with a population of 10 million, had just 2 optometrists for the entire country, while Congo and Madagascar, with populations of 4 and 21 million, had 0 optometrists. South Africa, on the other hand, which is a much more affluent country, had a good amount of optometrists. Thus, democratizing retinoscopy can have a significant impact on such low resource regions. Our proposed solution to democratize retinoscopy is a smartphone-based automatic retinoscope. We attach a smartphone behind a retinoscope's eyepiece to capture the retinoscope's video. Our goal then is to automatically analyze these videos to infer the refraction error of the eye without requiring a trained optometrist. To proceed with, let's look at the optics of the whole system. So we first start by modeling the optics of the retinoscope. In retinoscope, light from a source at the bottom passes through a lens and a beam splitter towards the patient's eye. Then it enters the patient's eye through the optical system of the eye and forms an image on the retina. This image on the retina now acts as light source in itself, and the light goes backwards again from the optical system of the eye into the retinoscope and through the beam splitter into the examiner's eye, and in our case into our smartphone camera. The image of this portion of the retina which is lit up is really the reflex which we saw in the videos earlier. We then formulated the whole optics of this forward pass of the light, the backward pass of the light, the camera, etc. And it led to a set of complex equations, but luckily for us, it simplified to give this reasonable simple formula you see here. I will not go into the details, but the main variable on which the refractive error of the eye depends was the ratio of the beam velocity and the reflex velocity. Note the very interesting observation here that our formulation does not require any lenses to achieve neutralization. And we can just look at the beam and reflex velocities and give the refractive power of the eye. Thus, we don't need the bulky lens kit anymore. Not only that reduces the cost and improves portability, but most importantly, it simplifies the process significantly. Now we can train even a lay person to just take this to move the retinoscopy beam around the eye and capture the video. They don't have to be skilled to understand what retinoscopy actually does. Now let's take a retinoscopy, take a look at a video of the retinoscopy and see how we can compute this reflex and beam velocity to compute the refractive power automatically. As you can see in this video, there are multiple problems. The first is that the beam moves on an uneven surface. There's the eyebrows, the eye socket, etc. So it becomes very hard to localize the beam. And the other bigger problem is that the camera itself is moving. As a result, we don't have any fixed reference point so that we can attach a world reference frame with respect to which we can compute the beam and reflex velocities. To solve this, we developed a very simple and frugal solution, a paper frame. The paper frame has these square markers placed at fixed places. These markers are called fiducial markers, basically a fancy name for any marker which can be easily detected by an image processing algorithm. Since the paper frame is fixed with respect to the patient, we can use it to localize a world coordinate frame. For example, we can place a reference frame on the top left fiducial and compute the beam and reflex velocities with respect to that. We next built a video processing pipeline to detect the fiducials, the beam, and the reflex. I'll refer you to the paper for technical details for anyone who's interested. And here is an example of our processed video. As you can see, the fiducial detection, the beam and reflex detection is quite robust. So here both sides of the beam has been detected, and when the reflex shows up, that get detected and detected robustly as well. So we evaluated our system on 185 eyes obtained from 128 patients. And here is a correlation plot of the predicted refractive error from our system versus the ground truth power obtained from subjective refraction. The mean absolute error of our system was around 0.62 diopters. And in fact, around 43% of our predictions had predictions which were within plus minus 0.5 diopters of the ground truth, while 74% were within 1 diopter. And here is a comparison of our method against clinically recommended manual retinoscopy and also the autorefractor. Although our current numbers are good enough to justify a screening device, as you can see, we still have some ground to cover against the clinical methods. We are working on techniques to improve our method further. Okay, now I'll change gears and move into the Smart KC system. So Smart KC is a smartphone-based corneal topographer for diagnosing an eye disease known as keratoconus. Again, this work was done in very close collaboration with doctors from the Shankar Eye Hospital. To begin with, let me explain what is keratoconus. So a typical human cornea is hemispherical shaped, but a person who is suffering from keratoconus has a cornea which is bulging outwards into an irregular conical shape. And the worst part is that keratoconus affects teens in the age group of 10 to 25 years and is the leading cause of blindness in that age group. And unfortunately, Indians are at a much higher risk of keratoconus, mainly because first we have steeper corneas to begin with, and second, the hot humid weather of India causes eye irritation, which leads to frequent eye rubbing, and this can result in the distortion of cornea. If detected early, keratoconus can be treated with prescription glasses and anti-allergy medication to not rub the eyes. As it progresses, however, surgery is the only option. And globally, around 27% of corneal transplants are performed just to treat keratoconus. Hence, early diagnosis of this disease is the key. Now let's take a look at how keratoconus is typically diagnosed. The main idea behind diagnosing keratoconus is to estimate the shape of the cornea. For that, a Placido disc is widely used, which is just a series of concentric black and white rings. This Placido disc projects a pattern over the patient's cornea, which are called Meyers. And as you can see, imagine that for a perfectly spherical eye, these projected Meyers will be circular and evenly spaced, and that will indicate a normal eye. However, a distorted cornea will result in a distorted pattern of the Meyers, and that will indicate a keratoconus eye. Though such paper-based Placidos are cheap, it requires an expert doctor, as using it is quite challenging, and even then it is not a very accurate method. The clinical gold standard for diagnosing keratoconus is what is called corneal topographers. These medical devices rely on the same Placido principle, but have a background light to have sharper Meyer projections. The captured images, there is a camera behind as well, which captures the images, and these captured images then go through an image processing pipeline to infer the 3D shape of the cornea. Though these devices are very accurate and do not require doctors, they are quite expensive, costing upwards of $10,000 and are not portable. Some of them, for example, cost as much as 10 kgs. The resulting Meyer images from these devices look like the one shown here. As you can see, visually it is very hard to infer which eye has keratoconus from these Meyer images. Hence, these devices output the curvature heat maps to help the doctors visualize the 3D shape of the cornea. For example, here the left eye has keratoconus, as is indicated by the high curvature at the bottom region of the heat map. Also, these heat maps help us in localizing the area of the cornea which is impacted by keratoconus, as well as the degree of the cornea. All this helps in deciding on the course of the treatment. So our goal in this work is to develop a low-cost portable corneal topographer which captures high-quality Meyer images and can output curvature heat maps. In short, our smart KC system comprises of 3 components. The first one is a Placido disc for the projection. Here we went ahead and 3D printed various shapes of the Placido discs. We iterated on the number and the color of the LEDs for the Meyer projection. And after a lot of trial and error, we finalized this design. Now I'll give a quick demo of the Placido attachment. There are some other minor innovations here. For example, the capsule shape design of the attachment allowed for enough indirect illumination from the LEDs. We used a simple butter paper as a diffuser for evenly spreading the light from these very bright LEDs, and also directly powered these LEDs from the phone USB to reduce electronics. And this not only brought the cost down and also kept the weight in limits. Okay, the next component of our system is to make sure that from this Placido attachment, we are able to capture high quality Meyer images. So when we started collecting the data initially, we found out that almost 40% of the data was not resulting in good ground truth curvature, good curvature heat maps. They were not matching with the ground truth. And apart from the expected out of focus and blurry images, we saw that even if we discarded those, and even for apparently good looking images, our results were not matching the ground truth. Since it was very hard to replicate these problems with real patients and thus debugging became a pain, what we did was we created a simulation environment where we could study and replicate these errors. On deeper analysis from this simulation setup, we found that our portable setup is causing misalignment between the Placido's principal axis as shown in the figure and the reference axis of the cornea. For example, when these axes were well aligned as shown in this figure on the top, we see circular and evenly spaced Meyers, and they result in the curvature heat maps like the one shown. This is a healthy eye example. However, in our case, due to the handheld nature of the attachment, we were getting misalignments between the cornea and the reference axis, either due to an offset as shown in the second image or due to a tilt as shown in the third image. In such cases, for the same healthy eye, we will get skewed Meyers like the one shown, and that resulted in incorrect heat maps. Note that to control for such misalignments, medical grade topographers have a head and chin rest for the patient and a table mounted setup for the topographer. The system we observed from our simulation was quite sensitive to these misalignments. For example, we estimated that even a 3-degree tilt can cause a 15% error in our estimates. So we wanted to solve these issues, and the way we went ahead was very similar to what Florian mentioned for the Remedio fundus camera, was to add real-time on-device image processing in the data collection app itself. So it performs the exposure and sharpness check, and most importantly, it automatically captures the image when the two axes are well aligned. This enables a minimally trained person to capture good quality images. And we noticed that once these features were in, our discarded image rate went down from 40% to 10%. Here is a video of our app in action. The app automatically clicks an image when the outer blue circle and the red cross at the center aligns with the Meyer center. Now we come to the final component of our system. We have captured the good quality Meyer images, and we now want to generate the heat maps. The first step is an image processing pipeline to identify the different Meyers and to label the Meyers. Once we have the Meyers identified, an arc step method, which is a traditional computer vision based method, is used to reconstruct the 3D coordinates of sample points on these Meyers. Next, we fit a smooth surface on these Meyers by using a least square fit via Zernick polynomials and obtain a 3D shape estimate of the cornea. The 3D shape can then be converted into curvature heat maps for visualization by the doctors. Note that another issue which came up was that the arc step method is basically a ray tracing based method where you shoot rays backwards. It requires accurate estimate of the 3D positions of everything, of where the Placido is, where the cornea is, etc. So one input needed was the working distance, which is the distance between the camera and the corneal apex. And it consists, as you can see from the figure, of three components: gap base, which is the distance between the camera and the base of the placido attachment, the length of the placido attachment, and the length of the gap top, which is the distance between the head of the placido attachment and the cornea. Although the gap base and placido length are fixed, gap top needs to be accurately computed for each input sample. Now let's see how working distance errors impact the computation of curvature heat maps. Let us consider a case where the arc step method has been calibrated to work with a fixed working distance of, say, 75 mm. This is actually the case for most clinical devices, where they ensure that the image is captured at a fixed working distance using expensive hardware like low depth of field cameras or even like laser sensors. And as shown in this case, for a healthy eye, we get nice symmetric Myers and the expected curvature. Now let's consider the case where the eye is captured at a different working distance. Example here, the eye has gone a little deeper into the attachment and the working distance is 72 mm as against the calibrated distance of 75 mm. In this case, although the Myers will be symmetric, they will appear much bigger than the arc step method was expecting at 75 mm. And this confuses the arc step method and it ends up incorrectly predicting a higher curvature. Again, from our simulation, we found that the system is quite sensitive to these working distance errors. Thus, we needed to incorporate a way to estimate working distance accurately without relying on expensive hardware. So coming back to that diagram, we need to estimate this gap top. For this, we relied on two properties of the human eye. First is that the radius of the human cornea is similar across individuals and even across age groups. And second is that even in advanced keratoconus patients, the shape of the cornea is distorted mainly in the central region. So the outer region of the cornea has the same radius even in keratoconus patients. This implies that for a given gap top, the radius of the Meyer reflections in the outer region will be approximately the same across all patients. Thus, we can have a one-to-one mapping between the gap top and the radius of the outer Meyer. So once we compute the radius of the outer Meyer, we can figure out what the gap top was. To learn this mapping, we use our simulation environment again and fit a simple regression model. Coming to the evaluation, we evaluated our smart KC system on 101 eyes from 57 patients. Around 1/3 of the eyes had keratoconus hair, and we asked 4 ophthalmologists to rate the curvature heat maps generated either from our smart KC system or from a medical grade topographer, Opticon Keratron. They were asked to rate into one of the 3 ratings: non-keratoconus, keratoconus, or retake. Here are a few qualitative results. As you can see, the heat maps from medical grade topographer, which are on the left, and from our system smart KC, which are on the right, look quite similar. Coming to the quantitative results, we achieved an overall sensitivity of 94% and a specificity of 100%. Sensitivity, just to remind, is the accuracy of identifying people who have the condition, in this case, who have keratoconus, while specificity is the accuracy of identifying people without the condition. Though our numbers look impressive, it is important to note that the medical grade topographer, which is Keratron, achieved 100% sensitivity. That is, it did not miss a single keratoconus patient. Although it had a lower specificity and did mark a lot of non-keratoconus patients as keratoconus. On the other hand, smart KC is missing a few keratoconus cases, and we are working on a few techniques to improve these numbers further. Next, we worked on a deep learning method to automatically classify heat maps generated from the smart KC system as either keratoconus or no keratoconus. This is allowed to allow for screening in remote areas where doctors may not be always available to rate these heat maps. Our method achieved sensitivity and specificity of 91 and 94%. What's next in Smart KC? We have demoed our system to the senior leadership team at Shankara and have received quite positive feedback. Based on these results, Shankara Hospital has agreed to scale evaluation to 5 of their hospitals. On successful trial, we aim for real-world deployment in Shankara rural clinics. We are also in early talks with Remitio for productionizing and getting regulatory approvals for Smart KC. To summarize, we have been working on low-cost smartphone-based systems to democratize diagnostics. Our goal for devices like Smart KC and Autoretinoscope is that all children in schools can be screened a few times a year by their teachers. Community health workers can do similar screening in rural areas, and even Zomato and Swiggy personnel can do home-to-home checkups in low-income communities in urban and semi-urban India. Thank you.
Thank you, Nipun, for such an exciting talk and sharing your amazing work with us. Also, it was very interesting to see how the system was improved based on the pilot feedback for further enhancements. So let me just wait for a minute to see if there are any questions. on the chat. But meanwhile, I do have a quick question for you. Just wanted to understand, given that this was collaboration with Shankara Eye Hospital, how was it to work with the doctors in this particular space, and how you could kind of utilize the domain knowledge while designing the system? How the feedback helped you improve the system? If you can talk a little bit about that.
Yeah, it was actually an excellent experience, and especially doctors at Shankar have a research mindset as well. So that really helped us to. So I mean, they were. I have to say they were quite patient in like understand helping us understand the physiology of the eye and making sure that we are doing the right thing. And there were a lot of iterations, like for example, when we went back to them with the heat maps, that okay, this is what we are getting, and they compared to the ground truth. They were, at many times they were able to say, okay, this is a flaw. This is not expected. So now we could get back to the drawing board. Especially, I mean, of course, they didn't know about the whole computer vision algorithms and all. But so at least their feedback helped us to go back to the drawing board and see where exactly the flaws were. For example, I mentioned about the tilt and the alignment, right? That was when like doctors at Shankara pointed us that this is a flaw which is not expected in this kind of eye. So we could sort of replicate that in the simulation environment and get back to them.
Hi Nipun, if you could just turn your video on for a few seconds. We are just taking snapshots of all the speakers. Thank you.
Meanwhile, I think, Nipun, we have one more question. So this is about the cost of the total device. So can you just comment a little bit on that?
So the cost of the device was around 2,500 rupees. And the main cost is basically 3D printing of the attachment. And we also used like off-the-shelf LED boards and all. We are improving the system right now. I mean, we use very cheap LEDs, but we are now having more like an on-device microprocessor to control the exact lighting and all. But even then, the cost is around 3,000, 4,000 rupees. And if we scale this further, right, we don't have to 3D print. We can use molding and all. So that will bring down the costs even down even further at scale.
Great. Thank you so much, Nipun. And now we would move to the third talk in this particular series. So I would like to invite our third speaker in the session, Zainul Cherniwala. Zainul is a co-founder and CTO at Tricog Health. He has been building the embedded systems and developing software over last 15 years. He's interested in the overlap of connected devices and machine intelligence to revolutionize and reinvent healthcare. He holds a master's degree from IIT Bombay and PhD from UCLA. Before Tricog, Zainul was a research staff member and research manager at IBM Research India, where I got an opportunity to work with Zainul as well. He has 7 patents and over 30 referred publications. So with this, over to you, Zainul.
Thank you, Tanuja, and thank you very much for the invitation, and good morning to everyone. Lovely to be here and to see the other talks also. It's quite amazing, Florian and Nipun, the kind of work you guys have done. It's fantastic stuff. My name is Zainul, and I'm part of a company called Tricog. We're about 8 years old. We've mostly based in Bangalore. Our engineering team has been working out of here. My association with Tanuja and actually another speaker on this, Deva, has been at IBM Research. And yeah, while I was in Bangalore, I met an intervention cardiologist who came to me with a problem, and we started working on an understanding of that problem. And sort of this presentation is sort of a story about some of that part of that journey. So I'm going to start off with talking about cardiovascular disease, which is the world's largest killer. It's well known that over 18 million people die of this disease every year. It's also a very expensive disease to treat. Over $1 trillion actually gets lost in the economy just in the US alone. And while this is, both an expensive and a critical disease, and this is actually very well known, what I didn't know personally was that a lot of these deaths are actually preventable. Now, when I met Dr. Charit, my co-founder and the CEO of the company, he narrated a story that has really stuck with me, and I like to come back to this story again to just remind ourselves what the impact of what we do. So this is a story of a 40-year-old patient of his. Originally, he had some chest pain. It felt like something that's something that has happened to him before. So he first waits at home, doesn't do anything. This is very normal for all of us. Then goes to a family doctor. The family doctor says, "Hey, you're perfectly healthy. Just go back home. There's nothing wrong with you." Gives him some injections. Things don't subside, and he goes to a nursing home or small hospital close by. They have an ECG machine. The duty doctor takes an ECG, says, "You know what? It's late in the evening. I'll contact my cardiologist, and you can come back in the morning and take a look at the report." Now it turns out that this pain is something serious. 4 hours later, he's just unable to lie down, and his wife is smart enough to actually take him to a large hospital. And as soon as they reach the hospital, they actually take an ECG. The cardiologist looks at it, and they realize he's having a massive heart attack. Symptoms were not completely specific on that front, but it's become so late that he doesn't have any pulse or BP anymore. 95% chance he's not going to make it, right? It's a very serious condition that he's reaching the hospital. Now it turns out that Dr. Charit was the cardiologist on duty at that hospital. They turn on the cath lab. They find that a major artery is completely blocked. That's the red arrow there. And they put in a stent. They perform this procedure that is called angioplasty, which is done in a catheterization lab, and they save the patient, right? So this is a great story, except that those 4 hours, he's left with a damaged heart. He can't even climb up 2 flights of stairs anymore without actually losing breath. Now, it turns out that this is actually the good part of the story. A lot of patients don't even reach the hospital on time. And this is not just one anecdote. There was a study done where they found that from the onset of symptoms to treatment in a country like India, even in urban India, this is a very large study across 20,000 patients. It takes over 6 hours to get the treatment that you need, and that's less than 20% of a survival rate. And when I met Dr. Charit way back 8 years ago, he was like, you guys technologists, come up with some way so that we can solve this problem, right? Give me an 80% chance of death to an 80% chance of survival. That's the challenge that we started this organization with. And so we dug a little bit deeper, and we realized that one of the big problems was that the diagnosis of these events and many other diseases starts with a very simple test called an electrocardiogram or an ECG. Now, it turns out that taking an ECG is actually a very simple process. It's not a very expensive device itself. It's about $1,000, and there are variations. You can get something as low as $500 and something as high as $5,000 and even $15,000. But about $1,000 will give you a good quality machine. But the problem is that the waveforms that come out of these need a specialist, need a person who's seen thousands and maybe tens of thousands of these waveforms to actually come up with the right diagnosis comprehensively and accurately. The reason is that every person's electrophysiology is actually unique. So every person's ECG is a pattern that actually identifies the person. It's a biomarker in some sense. And the other problem is that it is an approximation. It's actually picking up electrical signals on the surface of your skin, which is something that is happening maybe 2-3 inches below, inside your rib cage. So there's a lot of noise. There's a lot of different conditions that can happen. There's over 200 conditions. Now, there's enough work that has been done on computer-aided diagnosis in the past, over the last 30-40 years, in fact, but the accuracy of these has not reached the level of a cardiologist or an expert to be able to use in an unsupervised setting. So all of these algorithms that are even FDA approved, they're always labeled with the fact that this is a preliminary diagnosis and needs to be overread by a clinical expert. So what did we do? So we did 3 things. The first thing that we did was we realized that we needed high quality data. We didn't go down the path of building our own ECG machine, not until very recently. I'll talk about that in a bit. So we said, let's go after a high quality machine and figure out how we can get the raw data out of this. So we went with a company called GE Healthcare, a US based organization. We had some connections into their engineering team, and we talked about how can we get the raw data? And then we built this little device, the gray device towards the rear of the left side image, which we call the TriCog communicator. This is an IoT type of device which actually extracts the data. It's very simple. It's like a modem, and it encrypts it, compresses it, and pushes it to the cloud over whatever network is available. It works over 3G, 4G, or Wi-Fi, or even a 2G connection. The second thing we did was we created a bunch of algorithms in the cloud. Once the data comes there, I'll talk about this in a little more detail in just a bit. And then a third thing that we did, which was very important, was that we hired a bunch of cardiac experts. We have these people dedicated. We have a team of about 45 doctors today. They run this round the clock. We run this like a virtual hospital almost. They come in shifts. They're looking at this data in real time and overreading what's coming out of the algorithm and verifying whether this is correct or not. And the report goes out. So the way it works is that a patient comes to an ECG center. There's a cloud connected machine. The center hooks up the patient. The data is sent off to TriCog. A TriCog doctor looks at this data, does some magic, and then sends back an interpretation over our app, over email, and over a text message as well. One other important thing that we do is that if it turns out that the TriCog doctor finds that there is an emergency, a critical situation, we also contact the center doctor over a phone call and a coordinator at a hospital who can then contact a cath lab technician, a cardiologist, and even an ambulance operator and send the ambulance over to pick up the patient and send them to the hospital that they need to. And then all of this is done in 5 to 10 minutes, right? This is a very real time, very quick system that we've designed and we've been running. There's 3 things that are happening under the hood. I'll talk a little bit about each of those 3 things. The first is the IoT adapter, as I call it, the interpretation system and the apps. So the TriCog communicator has gone through multiple iterations. The first one we did was in 2015. Very rudimentary, very crude, off-the-shelf components. In 2017, we did something with one device, and then in 2019, we built a universal one that goes over multiple ECG machines, whatever has a digital output, whether it's serial, USB, Ethernet. We work with that. So we pretty much, by the time we landed into the 2019 era, we could access about 90% of the market out there. In 2021, which is last year, we even went down the path of building our own machine. There are very many reasons to do that, and one of those was supply chain of all things, and of course costs. The second aspect is our app. So we are a B2B system. So all our apps, interfaces, web interfaces, mobile interfaces, everything is for doctors. We are a doctor-to-doctor, if you may, service. And so, it's very unlikely that you would have seen TriCog anywhere out there. But the interfaces allow doctors to view their cases, view the ECGs, view the reports, coordinate with other doctors at other hospitals, and even track the patients that are in transit from one hospital to another. The third element is the AI engine. And the way this is designed is that every new ECG comes into what we call the TriCog Health Analytics Engine. And this is something that we've been working on for many years now, from the ground up. We started from scratch. And what it does is it takes the raw ECG and comes up with the algo output. In this case, it says, this is something medically relevant. It says ST wave abnormality, and there might be a lateral ischemia. Now, this output goes to the TriCog doctor. They're looking at the raw ECG, the algo output, and some annotations from the algo, and they're coming up with a final report. And in this case, the TriCog doctor said that the left ventricular hypertrophy, they missed a LVH and maybe an inferior wall infarction as well. And the final report goes out in 5 to 10 minutes. Now, under the hood, what's happening is that the TH engine is just a very large classifier. And that classifier has been built on the data store, and that data store is nothing but our own ECGs that are coming in the raw data and annotated by the algo, and most importantly, annotated by the TriCog doctor. And what our AI team has done is basically built a learning system that looks at this data coming in and goes and updates this classifier so that the next time this sort of ECG comes in, they don't miss the left ventricular hypertrophy. right? So how this is done, over a period of time, we've used multiple different tech stacks for the AI system itself. We started very quickly with signal processing, all of the expert systems that Florian talked about. And that actually gives us a very good base to begin with, because you don't need data, a lot of data for that. Then we started with shallow nets, and then deep learning. As we went on getting more data, we also figured out how to get cleaner data, how to annotate more cleanly, think about interoperator variability, lots of things that Florian talked about on the real world aspects of data collection and using that data in a real world setting for real sort of ML applications. I think all of those, I completely resonated with while he was talking about it. But that's where we've done, where we've gone. Over a period of time, we've actually exceeded most of the algorithms that we could get our hands on, that we could benchmark with. So it's gotten pretty good. We have our own US FDA submission happening sometime this year, in fact. I wanted to just talk about accuracy in a different way. This is across the entire gamut of all different diseases. But if you look at every single disease, there's something interesting that's happening. So this is a picture of the top chart is a histogram of the different diseases. I call it diagnosis number. So 0 to 200, because there are 200 different diagnosis codes. One thing I forgot to mention is that many times multiple diagnosis codes come in at the same time. So it's not just a 200 bin classifier. In fact, it's there's combinations of those as well. And the bottom chart is the F score, or the F1 score, for each of those conditions. And what I'm going to do is I'm going to play this as an animation, which shows how this has progressed over the last 2.5 years almost. So what you can see is that I'm just going to let it play once more, and see that over time, the green stuff, the accuracy is actually getting filled in as you go on. But I'll just go towards the end. What you'll see is that there's a lot of skew in the data. Probably everyone who's worked with real world data probably knows this, and especially when you have a multi-bin classifier like this, you've got a lot of data for some conditions and very little data for some other conditions. And that's really horrible for us, because this data skew itself is so hard to deal with from an accuracy perspective. That's one of the reasons we use the F1 score always to mention our accuracy. Now, the other thing is that the skew is not changing over almost 2 years almost, right? So we still have some data that we get a lot of. But the good thing is that the stuff that we get a lot of, we are actually getting very good at those, right? So 95, 98% accuracy. And then beyond the 50th most common condition, it's actually pretty bad, right? So it's all whites here. And of course, as we get more data, it's getting filled in. But there is a humility here, which is that we are not going to get as good as a human being. And so one of the things that we did very early on was that we realized that while the machines are actually good at the very clear normals and the very clear abnormals, we need the human beings to look at our borderline cases, what we are calling borderline cases. What we've done is we've built our algorithms with confidence measures. So we have thresholds where we can actually raise our hand pretty much to tell the human doctor, hey, please take over, because this is something that we don't know how to handle. The cool thing is that over time, the number of times that we need to resort to asking the doctor to take over keeps on coming down as our algorithms improve. Now, from a medical legal standpoint, we do 100% overread for all our ECGs even today, but we are actually good enough that we can turn that off if the legal agreements allow us to do so. Now, the nice thing about all of this is that we can really increase scale without increasing the size of our own doctor teams. What used to take of the order of 5 and 8 minutes before takes less than 30-35 seconds today on a per case basis. Now, we've been able to scale this over many locations, thousands of locations in India and other countries. Over 9 million actually patients that we've diagnosed. We are doing about 250,000 patients a month today. 4% of pretty much all ECGs done in the country flow through TriCog today. That's our estimate. We don't know that for sure, of course. But over a quarter of all the cath labs where these angioplasties get done have become customers for TriCog now. So it's something that has to be done at scale. We've designed it, and of course the AI helps us build that scale. The kinds of customers that we have are small clinics, like a single doctor clinic, a mid-sized hospital, which is on your top right, and even enterprise and diagnostic chain customers. And now we've even in the last couple of years gone into government contracts. We have 4 state governments that we work with right now, and pretty much the entire cardiac screening program for the state government is run by TriCog today. A few logos, people from India who visited these hospitals. Somewhere in the background, TriCog is at work. And these are different segments and how those segments have grown. You can see a very clear dip during COVID. That's our COVID dip. That did happen. We were like nice meteoric rise, and then boom, COVID hit. But it's coming back up now, and it's become pretty good. We are not just in India. We are in 12 other countries, including in Southeast Asia and Africa, and recently in South America as well, Central and South America. So it's growing. I think a lot of the same sort of needs that we see in India are also in many of these other regions as well. So that's what's happened. Now I wanted to just give a snapshot of what some of these critical ECGs. So this is a picture of an ECG. Kind of ECG that comes to us, right? This is from a 45-year-old, 7 o'clock in the morning. And if there's a doctor in the room, they'll say, oh my God, there's something really bad happening in the V1, V2, V3 leads, which is this bump here, which is called the ST segment. Now this is coming from a place like this, right? This is in a place near Bhopal, which is in central India, a place called Hoshangabad. And this is this New Pandey hospital that is sending us the ECG. We send out a call to the nurse. She's all alone. She's like, I don't even know what to do with this patient. Is he going to die in my hospital? Like, okay, just cool down. Just give them this medication, and then they were able to send them off to Bhopal. And this patient had a good story. His life was saved. Another one is a 32-year-old. This is a very, very strange case. This is happening in a clinic inside a factory, and the nurse is calling us saying, "Look, there's a problem with your machine. I'm getting all noise." And we realize that, goodness, this is not noise. This is actually a very serious condition called a ventricular tachycardia. The person could go into cardiac arrest very, very soon. And they were able to get an AED, a defibrillator, and actually revive this patient. They were sent to a larger hospital, which is about 20 kilometers away from the factory. And this is happening on a Saturday. The gentleman, this 32-year-old, right? He's the breadwinner of the family. He's back to work on Tuesday. So that's again a good story. Third one, which was interesting, is an old elderly gentleman in Mysore, which is close to Bangalore. And this is almost a heart that is not beating, but the person's feeling fine, except for the fact that when they go out for their evening walk, they just can't walk fast enough anymore. And we realize they have complete heart block. They need a pacemaker. That's the diagnosis that was done for this. And they got the pacemaker, and of course, the person is okay now. This company was formed with a bunch of, the doctor, of course, on the top left, Dr. Charit, Dr. Udayan, who runs the data science team. I run the hardware team at TriCog, and Abhinav, who is our software architect. We've had the pleasure and privilege of having fantastic, investors all through, and we've got great support from them. We've got 2 other guys on our leadership team who run businesses, Samir and Sandeep, who run international and India business for us respectively. That's pretty much all I wanted to talk about. This is sort of the philosophy behind TriCog has always been about this virtuous data cycle, getting more data, getting better algorithms, higher productivity, improving this flow, and just getting more patients to be able to experience that accessibility and the virtual cardiology at scale, pretty much a cardiologist at your doorstep. Our big audacious goal is this. This is a slide that haven't changed in like 8 years, and this is the dream where we'll be able to predict ahead of time that there's something wrong with you. Just getting the ECG is not enough. So we've got a pathway. We've started with the ECG. We have gotten into ultrasound. We've gotten into point of care ultrasound and continuous monitoring and even remote health management. And that's how we are getting better data, richer data. We are building our algorithms today on new data that's coming up. So yeah, thank you very much, and thank you for listening.
Thank you, Zainul, for sharing your work on this very important and common issue of heart disease in society that we see often. It is also interesting to see how you have incorporated the approach of human and AI collaboration to increase the efficiency and accuracy of overall system. So let's see if there are any questions on the chat.
I have a quick question. This is Amit. So I have a quick question, not directly related to the technology or something. So this is like a startup, and there are. I mean, most of the time, a lot of the startups that we hear about are more in the so-called IT space, right? And this is more in the healthcare space. Obviously, this community is working in the healthcare space. How do you what's the like how easy, difficult is it to raise money? Is there buy-in from whoever funds them? Is it the same as other startups, or this is a completely different class which is maybe more difficult or more easy or whatever?
It's a very interesting question. Very yeah. There's lots of different answers. I think the first one is that from investment perspective, there are generally two types of investors. There are financial investors and strategic investors. Financial investors are people who are looking to get a return on their investment based on whatever their return rate threshold or target is. And those people don't really make a differentiation whether this is a healthcare startup or a fintech or an edtech startup. Of course, there are some that are very sector specific, but then some that are sector agnostic. Some that are more B2C, some more that are B2B. Then there are strategic investors. As of now, we have very few strategic investors on our investor board. But strategic investors are looking at products that strategically fit within their product ecosystem in some way or the other. And usually strategic investors are not funds, are companies themselves. So it's easier to raise with strategic investors, but it's also hard to find alignment with them. Financial investors are far easier to raise money from, if you may, because they are also mostly sector agnostic. But as long as you're growing, no problem.
Thank you. Prashant, you're on mute.
Yes, hello to Zainul.
Hi, Prashant.
Great. I think you just 2 pointers. I think I've been following you from your IBM days till you kickstarted Trigog to now. I think wonderful journey. A lot of inspiration for us.
Much, sir. No, thank you very much, sir. And pleasure meeting you and seeing you all again.
Sure.
A lot of old friends here.
Great.
So I see one more question on the chat from Nipun. So he has said that, what are your thoughts on the medico-legal frameworks? They are, of course, well-intended, but at times they seem to come in the way of saving lives. What do you think is the right compromise safeguards going forward?
Okay, that's a great question, Nipun. On our side, because we are, I guess, so tied down to the clinical side of the solution, the medico-legal side doesn't come mostly in the way for us because we have our own doctor teams. If we were doing a clinical decision support system for others, that's where medico-legal becomes a little bit trickier. But because we have our own doctor teams, and the cool thing is that doctors, they take liability almost by default, right? That's their job. In fact, that's the job to treat patients, right? So it's from a medical legal standpoint, it's all about liability. It's all about patient liability and safety. And doctors, they never hesitate in taking liability. In fact, they want to, and they are like, please let us do our job, right? That's the way that they sort of work. It's us guys, the technologists who are like, oh my God, what will a doctor do? How will we sort of deal with this? It does become tricky when you want to go, the autonomous stuff like what Florian talked about, which does not have a clinician in the loop. That's when it becomes tricky. But that's also, again, when what I've seen in a lot of FDA submissions is that they just label it and say, look, this is not for diagnostic use. It's only for informational use. Things like that. They'll couch things like that, and you just go forward. And over time, what does happen is that the technology does get used, and does get used in the right way. Of course, it might get misused in a few instances, but by and large, it's okay.
Thank you, Zainul. And with this, I would conclude this session. Also, like to thank all the three speakers for all the amazing work and the talk for sharing with us. And thank you for, I think we are exactly on time with this session. So now I would hand it over to Chetna for the next session, and she would also talk about the housekeeping and the break, 15 minutes break. So over to you, Chetna.
Thank you, Tanuja. Good morning, everyone. So we are on time actually on the completion of first session on healthcare, and the second session will be on sustainable living, and we have two sessions in that. So we will take a break now till 11:30, and we will be back and we'll start the session at that time. Thank you.
Maybe we come back at 11:25. That way we'll have a little buffer because people will always flow in. So, and by 11:30 we'll get started.
Yeah, sure.
See you in 10 minutes. Bye. Hey Deva, welcome.
Hi Deva, welcome.
Deva is still on mute. Can't hear him right now. Deva, we were able to see your presentation momentarily. Now it's blank screen.
Deva, you are on mute. We are not able to hear you.
Hi.
Hey, hi.
Morning, Chaitanya. Morning.
Good morning.
Hello, Deva. Morning.
Morning, Prashant. Good to see you again.
Good to see you again. How are you? Long time.
Doing all right, and you?
Like as usual.
That means grand. For
No,
Prashant,
no,
it cannot be anything less than grand.
no. Life as usual, simple. Nothing great. But great to see you back here. It's been a long time. Yeah.
Sorry?
I said it's great to see you in this forum. I think it's been long we physically met or connected also. Yeah.
That's right, yeah. Good to see you too.
Okay. I'm switching myself off. So yeah, over to you. Sorry, I just came in to just say hi. Yeah.
No, thank you. It's very kind of you.
We will wait for another 2-3 minutes and then we will start the session.
So Deva, I know, has a train to catch, I think. So we should be well in time.
No. Actually, I moved the time, so I thought like I moved the appointment to tomorrow, so I didn't want to rush the things. So
where are you now? Where are you located now?
in my hometown, I'm from Coimbatore in Tamil Nadu.
From Coimbatore, okay. So, and you were saying you were going to Chennai, right?
Right, yeah.
How far is it?
About 400 kilometers, overnight train journey.
I think people are joining, so we will wait for another 1 minute and then we can start.
No worries.
Thank you.
I'm very impressed at how you guys are running things on time. You're counting minutes, which is good.
No, we intentionally put in a break in the middle. That way, any buffers would overflow there. But the earlier session speakers were dot on time, so we didn't need the buffer.
Oh, okay.
So Amit, shall we start?
Can you please introduce the speaker and we'll get started?
Yes. Yeah. Hi, good morning everyone again. Welcome to the symposium on AI for social good and sustainable computing. So I am Dr. Chaitanya here. Let me introduce this, today's speaker for this particular session now. So we will be having the session 2 with 2 slots here. Deva P. Sitaram, who will be talking about reinforcement learning for efficiently cooling the buildings. Welcome Deva for this particular session. So let me introduce Deva. He is a serial entrepreneur and inventor and a scale-up advisor. He has been working in sustainability technologies such as distributed energy resources and water for more than a decade. He holds an MS from MIT Media Lab. Thank you, Deva, for accepting our invitation and be here for sharing your knowledge. Over to you. Thank you.
Yeah, thank you, Chetna. Good morning, everyone. Thank you for inviting me to give the talk. So I'm going to be speaking about using reinforcement learning for efficiently cooling buildings. The work was done by Saksham, Akshit, Liston, and myself. I see Akshit is here, and the other colleagues also might be here. So we also acknowledge the inputs and guidance from all our colleagues listed here. So let me give you an introduction of the problem, right? The commercial and residential buildings consume about 34% of all the electricity generated in India. This amounts to about 450 terawatt hours of electricity consumption, and around 40% of that building energy consumption goes into space heating and cooling. This slide, changing slides. When you look at it, even when you assume only the 50% of the electricity consumption, the 454 terawatt hour that I mentioned, is coming from coal power plants, it would still lead to 100 million tons of carbon dioxide per year based on the EPA.gov calculation. Why am I saying 50%? Is that, when you look at the power generation portfolio, are you able to see my cursor?
Yes, it is.
Okay.
Yeah.
So about 73% of all the electricity is generated from coal power plants. And even if I assume only 50% is generated from coal, it leads to 100 million tons of carbon dioxide. So this is a serious problem. So at Smart Joules, we said, okay, what can we do to help the commercial buildings improve their energy efficiency, thereby cut their electricity bill and also carbon emissions? So we take a three-pronged approach. We go to the commercial buildings and we look at the design, how can we operate the different energy guzzlers more efficiently? What would be the optimal design? Which are the equipment which are energy inefficient and replace them with efficient equipment? And also, how can we optimally operate those equipment? So this is the three-pronged approach we take to do this. In this talk, I'm going to be primarily focusing on the operations part, right? And the company has been doing very well, and it has customers in pretty much all parts of India. And recently, we expanded into Indonesia. And currently, we are focused on the hospitals, which are both only the OPDs and also the ones which have inpatients, right? So the background, right? So when you look at a typical energy consumption of a building, of a hospital, let's say we take a hospital which is 55,000 square meter in floor size. In Kolkata, it consumes about 250 megawatt hour of electricity on a monthly basis, right? And around 49% of the energy is consumed by the HVAC high side. I will explain what HVAC high side is in the next slide. So the key numbers you need to remember is the significant consumption is the HVAC high side. So when you look at air conditioning system, a centralized air conditioning system, this is how it works. It takes the heat from the hospital inside or the commercial building inside and brings to the cooling coil, and then the cooled air goes back into the building. Now there is a chilled water that what it does is that it takes the heat, just a simple thermodynamic heat exchange. By being circulated in the cooling coil, it absorbs the heat from the hot air. It becomes hot and goes into the evaporator, right? So then it exchanges heat with the refrigerant and comes back as cooled water. And then the refrigerant takes the heat from the chilled water and goes into the condenser and transfers the heat to the water. This is a separate water supply, and goes into the the cooling tower, which is the environmental condition actually, right? and then the cooled air gets circulated back into the building. So in all the downside loops are all cooled, and the top side are all heated, right? And then each one is circulating within this loop. So the refrigerant circulates only within this loop. The second water supply circulates only within this loop, and air goes into this environment, right, in the outside environment. So an abstract diagram, you can see this is the low side that goes into the hospital buildings, and this is the high side, and the cooling tower is usually on the top of the building. If you folks work in STP, you can go to the top of the building. Say for instance, in the Manyata Tech Park, you will see on the top of the building, and then there are condensers, and there are the plant rooms. Some of these equipments are inside, and this is outdoors, so that the heat can go into the ambient air. So what is the optimization objective, right? Transfer as much heat from the building interior to the outside environment, right? And you use as little electricity consumption as possible. How can you do that? Is you adjust the various levers. How do we pump the water? If we pump more water into the cooling tower, more water will get cooled. Or we run the cooling tower fans faster, more cooling will happen, and so on and so forth. So those are the levers we play with to achieve this objective. So the objective is actually kW per TR, that means kilowatt hour per tonnage of cooling. If the ratio is small, anything less than 1 is great, smaller it is better. Currently, Smart Joule's target is about 0.72. That means you use less energy and get more cooling out of it. So how do we get this thing, right? So we tried multiple approaches. The first one is the PID controllers. A PID controller has 3 parts. Let's say there is a desired state and there is a measured state. Let's say if you want to maintain the temperature at a particular state, the proportional control, what it will do is it will look at the desired state and the measured state and look at the delta between it and give a control signal which is proportional to the error, right? Or you can understand it from a cruise control in the cars, right? Let's say you want to you're pressing you have set a particular speed, and the cruise control has to maintain it. So let's say there is a difference between the set speed and what is the current speed. Based on the level of error, it will make a proportional change to the control signal. So the problem is when the error becomes small, it may not be sensed by the proportional controller. So to address that, we have an integral component. What it will do is it will accumulate the error over a period of time, and the error becomes larger. It will give a control signal in response to it. And then the third one is any sudden change. Like let's say your car is going and then it hits a slope or a huge speed bump. We have thousands of speed bumps in Bangalore, like one of those hills. It has to rapidly adjust it. So that is a differential component. So that's why they are called proportional, integrative, and derivative or differential controllers. And there are 3 constants, the Kp, Kr, and Kd have to be adjusted to make sure the desired state and the measured state are as close to each other as possible, right? So it's a very mature technology, and people in the building automation space know it very well. It has been around for more than 100 years. But the problems are it requires manual tuning of the parameters and does not work well when the measured state moves far from the desired state. And it is not easy to manage multiple components and constraints. Like I showed you, right? There are condensers, cooling tower pumps, and so on and so forth. It's difficult to control it from one PID or multiple of these PIDs and make them coordinate with each other, right? So then we tried, okay, we all come from the computer science, and if you're a computer scientist, you have to have a little language, at least a little programming language in your belt. So as per the statistics, most of the PhD theses are about programming languages, right? So what we did, we tried a little language. It takes little, conditions, evaluating conditions. In this case, we say, the set point chiller temperature is less than 7.5, or it is greater than 7.6. You adjust the set point temperature to 7.5, right? So we have to write recipes. We call it the Joule recipes. So where, there are conditions like this, And this is inspired obviously by the IFTTT, it's a very popular platform, and based on that, we created this. So what are the pros and cons of the Joule recipes? What is great about it is very less expensive, no additional hardware required. It's very simple, application specific, little language. People who are not, programmers, especially the building analysts, energy analysts, can write this code, automation code by themselves. But unfortunately, it is not composable, right? I mean, these are obviously not Turing complete languages. You cannot call one recipe from another recipe. And actions and conditions are not interweaved. So each action requires a separate recipe, and not scalable because it requires manual development and deployment and maintenance for each of the conditions, whatever the things that in the hospitals. As you know, hospital operation is very complicated, right? So then we said, okay, let's look to the AI. As we all know, AI is the big thing now. We have to try that, and in particular, the reinforcement learning seems like a good fit. And so there are agents. What it does is that it has the following control actions. It can adjust the VFD frequency. VFD stands for the variable frequency drive. Using the VFD frequency, we can adjust the frequency of the motor or the speed of the motor. And when you look at it, the frequency F1 by F2 equals to P1 by P2 cubed. So that means if I increase the frequency, the power consumption increases cubically, right? So that is what the agent can do. And the actions it can take on the environment are, it can take those actions, and the environment will change in response to those actions. What is the condenser entry temperature? What is the wet bulb temperature? What is the data, etc. Based on what is the change in the environment, the agent gets a reward. Let's say if it achieves the objective, it gets better reward, and if it doesn't, it almost like your performance review. You set your performance goal for the year, and if your manager is nice, she will give you a good reward. If she is not nice, she's not going to give you a good reward, right? But in this case, there is no subjective component. The agent achieves its objective, it gets a reward. So when you look at the target, the reward function, we are using the exponential recency weighted average method. What we look at the reward function is, it is a function of this one, the target condenser water entry temperature, prior condenser water entry temperature, minus what is the target condenser water entry temperature minus after the condenser water entry temperature. So what before and after means, before the action taken for the last 5 minutes, it's averaged over the last 5 minutes. What was the condenser water entry temperature? You might ask me, what is the condenser water entry temperature? So the condenser, the point at which the water is entering the condenser, that is called the water entry temperature. If it is cool, then the condenser will work less. So that means it will consume less energy. How do you get condenser water entry to come down? You pump more water into this cooling tower, so it can push more heat out to the environment. You can also run the cooling tower fans at a higher speed, so it achieves the cool down, the cooling that you required. So the cool down water comes down to the condenser. So that is the idea. You adjust this, the pump frequency, the condenser pump frequency, and the cooling tower frequency, and then you measure this. And then what we do is that is the mean of condenser, as I already explained, mean of condenser water entry temperature after the action for 5 minutes and before the action for 5 minutes. So why did we choose RL, right? So what happens is it can learn from the interactions with the environment, and it can hit the road running in new buildings. So for us, we get paid as a function of the energy savings, and usually no historical data is available. So we have to hit the road running. So because it doesn't require, it's not supervised method, it's not an unsupervised method. It just learns from the environment and the model, and it can improve itself. So that is why we chose RL. And it can efficiently run on resource-constrained embedded computing devices like Raspberry Pi. And, as you can imagine, the hospitals managing energy is a non-linear and a non-stationary problem because the occupancy varies all the time. There can be, surgical procedures going on, emergency procedures going on, and the equipment health and weather conditions are changing with time. So we need something very adaptive. And it can scale to multiple input and multiple output systems, as I will show in a bit, right? And then, we evaluated, in a hospital, again in the Kolkata hospital, we said the learning rate for the reinforcement learning is alpha is 1, and condenser water entry weight is 0 to 1. So we looked at, there are two objectives. We can do the cooling as much as we require, but if we consume so much of energy, we are missing the real objective, right? We are missing what we need to do. So that is not okay. So we have two objectives. One is cool it, and other is energy consumption, how to reduce energy consumption. So we give two weights. One is for the water entry temperature, and other is for the energy consumption, 1 minus of the weight that we give to the other one. And then every 5 minutes actions are taken, and discount rate gamma, it is an exponential recency technique. So obviously the older actions get older rewards get older weights, less weights. Older reward gets less weights. And the set point and target is computed in real time. And there is an important concept called the wet bulb temperature, right? I mean, this will come up again and again. So wet bulb means in these buildings, the temperature is measured using two things. One is a wet bulb. So wet bulb is, when they say bulb, is even if you look at the old mercury thermometer, the mercury is in the bulb in the shiny part. And if a wet cloth is put around the bulb, and you measure the temperature because of the humidity, that is called the wet bulb temperature. And the dry bulb, there is no towel wrapped around it, and you measure it as it is. So the wet bulb temperature actually accounts for the temperature even with the humidity considered. So on a rainy day, the wet bulb temperature and the dry bulb temperature will be same because of the humidity. But if that is not the case, your wet bulb temperature and the dry bulb temperature will be different. But we have to get the cooling with respect to the wet bulb temperature. Again, the same diagram, right? I mentioned that, take the heat from this side and pump it out to the environment here using just a simple thermodynamic heat exchange. And one key thing I forgot to mention is when the difference between the hot water and the cold water is very high, the simple law of thermodynamics stays, it will easily transfer the heat from the hotter substance to the cooler substance. So that is what, if the more cooled water or the cooled refrigerant comes down, the heat exchange will become easier. So then, we looked at, so when you look at it, so we said we'll simulate this and test out our algorithm. So this is the red line is the set point temperature or the target, and the blue is the condenser water entry, and the green is the VFD frequency. As you can see, whenever the temperature, the measured temperature goes above the set point, the VFD frequency increases. On the other hand, when it goes down, the VFD frequency reduces. So here in this case, it went down here. The VFD frequency is adjusted to respond to that, right? So then we said, okay, simulation is all good, but it is not the real thing. So we have to put it in a real life and real life situation on site and check it out. Here, what we do is that, this is the target temperature, and this is the condenser water entry temperature. So in this plot, it is reversed. The red color line is the target, and the green color line is the measured temperature. And we adjust the various frequencies, condenser pump frequency and condenser pump 2 frequency. And there we are adjusting 3 condenser pumps and 3 cooling tower pumps, right? So what we saw, when we don't worry about the energy consumption, what it does is about 90% of the time, we look at these two slices, the blue slice and the orange slice, the VFD is able to achieve the set point temperature within plus or minus 0.5, 90% of the time. But we are not looking at whether it is optimally doing it or not, right? So now then we said, okay, we have to look into, also the energy consumption. But here in this case, we said we will give more weightage to energy optimization, right? We have to reduce the energy. It is it's like some of the corporate budgets. It is not about achieving the action. There is a budget. That's it. You can't fit it into the budget that goes out the door. Whatever the project plan you have. So like that, in this case, one key thing is that we are not controlling the temperature in this simulation. We are keeping this curve as it is, and we are, simulating the VFD to see the reinforcement agent and the VFD to see whether it is bringing down the frequency. So at this point, even though the condenser water entry temperature is more than the set point temperature, the VFD frequency is not increasing because it is giving more weightage to energy. It says, too much energy is being consumed. I'm not going to adjust the temperature. On the other hand, we say, in this case, we don't worry about the energy. We want to achieve the target. So as you can see, when the measured temperature goes above the set point temperature, it immediately ramps up the VFD frequency so the cooling can happen. So, and one thing is above 50 Hertz is only an artifact of simulation. The VFDs don't go beyond the line frequency of 50 Hertz in India. When I say line frequency, I mean the power line frequency. So next one, what we did is we give 20% for the energy weightage for energy consumption and 80% for the condenser entry temperature. So obviously, it slowly increase the VFD frequency because it has to give consideration to the energy consumption, but it still attempts to reduce the measured temperature so it can come as close to the set point temperature as possible. So then here we took it to a real life, and we said we are going to look at the condenser pump frequency, and then the condenser water empty temperature and the target. So as you can see, this is the target, and this is what is measured. So when it goes up, it rapidly. This is the maximum it rapidly ramps up the frequency. It is running at very close to the maximum of 40 Hertz for this VFD, and when it is so in this case, it has overachieved. So it rapidly brings down the frequency. So you might ask, why did it overachieve the target? Why did it overcool? As I said, the wet bulb temperature changes rapidly because of the environment, or occupancy changes. Suddenly, a large number of people left, or an operation completed. So in those conditions, we might overachieve the target, so that in response, it is reducing the frequency accordingly. And in this case, when we are also considering the energy consumption as a factor, we are able to hit the target 57% of the time. And the remaining time, it is exceeding at different levels. You can look at it from this, the table. I don't have the time to go through each of the points. So the discussions and the future work, right? I mean, energy efficient cooling solutions is very important. And what happens is we are going through a strange feedback loop because of the climate change. The environment is becoming hotter, and you use more HVAC, more energy usage, more refrigerant usage that heats up the environment more. So it's important that we address this problem very efficiently, and so that this feedback loop is broken. And as I already mentioned, it was able to achieve the target 90% of the time when energy consumption was not considered. When it was considered, it was able to achieve 47% of the time. And we are going to do fine tuning of the multi-objective model. We are also going to try different reinforcement learning algorithms. And, it can be a potential solution for automation of assets in the high side. And there is a bunch of related work. And to the best of our knowledge, what we have seen, people have not combined the both, that achieve the target while reducing the energy consumption. We have not seen this, in some sense, conflicting goals being addressed. And these are a few references. So I will stop here, as Amit would like me to, so that he can maintain the schedule. I'm sorry, and also Dr. Chetana. Thank you, folks. Open for questions.
Thank you, Deva, for such an insightful talk. Any questions from the audience?
I have a question. So this is more from an implementational point of view. So this is all well and good. How do you like work with the energy department or something to actually maybe get this more widespread or things like that? Have you interacted with the governments and energy companies?
We actually, no, the utility companies don't worry about this. When you say energy company, I think you mean the distribution companies. They don't worry about energy efficiency, etc. Okay. So we go to the consumers, and the good thing is everybody wants to reduce their electricity bill. And in the model, actually, so that is why we are taking a three-pronged approach. We replace the equipment, we bring about design changes, and they are able to get the return on investment very, very quickly. We are not just focusing on the software. I mean, so it is not a pure software only approach. So that is why we are able to get the ROI immediately. The payback period is very short.
But given the fact that, I mean, energy is becoming increasingly, I mean, we hear about it in the media, every country is kind of facing issues with keeping up with the energy demands. Is there any, or do you see interest from the government side, from the utility companies, any kind of interactions that you have with them?
So, not really for the energy efficiency part, okay, because for them, it is not about reducing the consumption, because you consume more, they make more money, right? So, the money is God, right? So they worry about like their balance sheet and how to be as profitable as possible. So they don't worry about, increasing the energy efficiency or anything like that. So that is not, maybe they are interested for their own buildings to do that. But, when you go to a typical office buildings, the consumption is not as high as where there is a big HVAC system, or, there is more occupancy, etc. So that is where it is. So we are, so that's the answer.
We have one question here from Sindhuja. How were the value functions and the reward distributions when the idea was formulated, decided upon? So she is asking in the perspective of data science, because she is pursuing it on reinforcement learning as one of the subjects. And she is also asking, is there any paper where the theoretical part was discussed for this, and any use case, to learn more about it?
So the references are listed in that slide, right? Sorry, you went very fast. So what were the two questions that she asked? The one is the parameter, and what was the other one?
Yeah, how were the value functions and the reward distributions when the idea was formulated?
Yeah, so what we said is like in terms of the reward function. So obviously the value function is very clear, right? We want this to bring down the temperature as much as possible. Hey, you reduce the temperature, as I showed in this diagram. We have to bring this down, this part, as cool as possible, because this part is only the environment. How many people are there? This is the usage, and this is what is under our control, and we want to do it with as little energy consumption as possible. So that was the value function that we had. And then the rewards were, we said, okay, initially 0 for achieving the target and 0 for not achieving the target and 1 for achieving the target. And when we brought in the multi-objective thing, then we said we will give weightage. It will be weighted. The rewards will be weighted based on how much is the target achieved with respect to cooling and with respect to energy. And obviously, this is an iterative process. It is not like there is a magic number. We have to adjust and see how can we get this value and the rewards. So that is what we are trying it out. So and the references, the paper is listed. This is not our paper. We have not published any papers around this. So yeah, so this one gives a very good idea of that. The first one, the one by Biswas et al.
Yes, thank you, Deva, for such a wonderful session. And in fact, I missed to ask you in the beginning. So we were recording these sessions. So I hope you are okay with it.
Yeah, that's okay.
Yeah, thank you so much. Thank you.
Have a good day. Thanks everyone for listening. Appreciate it.
Thank you. So now we will move on to the second session here by Ganesh Shankar. The topic is IoT and data science in clean tech. So I hope Ganesh is available. Yeah, hi Ganesh, welcome.
Hello, Dr. Chetna. Can you hear me?
Yes, you are audible. Thank you. So let me introduce Ganesh. Ganesh Shankar is a serial entrepreneur in sustainability and clean tech space. He is currently the founder and CEO of FluxGen Technologies and adjunct faculty at the Center for Continuing Education at Indian Institute of Science. He has also co-founded the Sustainability Engine Foundation, a Section 8 for impact organization with a mission to multiply the impact of sustainability leaders through goal-oriented collaboration. And also he co-founded Airprobe.tech, which is a drone analytics for solar farm fault inspection. He has been with GE Digital Energy, Telco Solar, and Next First Technologies before embarking on an entrepreneurial journey. He is an alumnus of Indian Institute of Science, Bangalore, and has done executive education in the entrepreneurship at Huss School of Business at the University of California at Berkeley. He enjoys long distance cycling tours. He regularly does national holiday cycle rides, which include Bangalore to Goa, Bangalore to Mangalore, Calicut to Kanyakumari, Mangalore to Goa, Goa to Mumbai, etc. So this is a brief intro about Ganesh. So thank you, Ganesh, for accepting our invitation and being here to share your knowledge today. Over to you. Thank you.
Thank you, Dr. Chetna, for the kind introduction. I hope you can hear me.
Yes, we can. Ganesh, is that okay? We record your session. Are you okay with that?
Surely, Dr. Chetna, please.
Thank you. Thank you so much.
I should say I consider Deva as my teacher, and this is Teachers' Day month. So I don't know how much value I can add when my teacher has already spoken before me. So thanks again for inviting me for this talk. I would like to share my screen, and please kindly let me know if you're able to see my screen.
Not yet.
Is it
Yeah.
visible?
Yet to load.
Coming up, not yet.
Yeah.
Yes.
Now it's visible.
Yeah, adding to the fact that this is a month of Teachers' Day month, I come from a family of teachers, and a lot of my learning in building a startup or being in entrepreneurship comes from the fact that I didn't have any knowledge of building a company. And being from a family of teachers, we always thought about sharing knowledge, not building companies. So this presentation is not just only about the topic IoT and data science and clean tech. It's also a bit about my own journey in this space and how I looked at it. So I'll try to talk about the nitty-gritties of the challenges from looking at from a socio-economic point of view. Initially from a problem solving purely from a social science point of view, and then solving from a holistic understanding of entrepreneurship. So kindly excuse me if there is a bit of noise around here because I'm at a conference where I'm also exhibiting. So hope I'm audible and clear.
Yes, it is very clear. Thank you.
Okay, that's great. I think the noise cancellation algorithm of Cisco FX is working very well. Okay, so Yeah, this is an outline. I'll just bit about share about my how I started all this thing, and Deva has already touched upon some of the aspects of how do we actually are creating climate crisis, and he's talked a wonderful solution of what Smart Geols is doing. Having been associated with Smart Geols in the past, as I'm really thrilled about the work that Smart Geols is doing, and I would like to add from a point of view from a distributed energy generation and distribution, and then looking at something in solving the problem of water and some case studies, and I will eventually conclude. Yeah, I mean, I did while I was doing my master's at the Institute of Science. I always felt that I'm getting all taxpayers' money, but I'm not really contributing much. And of course, I was working on something related to a quadrupole ion trap mass spectrometer, which is used in even building quantum computers. But I realized that I should do something that is more useful to society immediately. However, I got a job in GE aviation system, and then I moved to GE energy business. That's when I started thinking about I could do something that makes sense at a ground level. This was in 2010. I left my job in GE Energy. We had developed energy meter for Australian market to do digitize the utilities at that point of time. Yeah, and then that's when I got my initial understanding on energy, to an extent on climate change, and how we can apply data to solve the problem of something as important as energy and water. My initial interest was in clean tech in energy. That's why I worked with a company called Celco Solar. The picture that you're seeing me standing is where I was a commissioning engineer for Celco, which was primarily involved in rural electrification project. This project, of course, was a project where you would be powering a water purifier system to give water to the pilgrims coming to this pilgrimage center called Dharmasthala. So it was an interesting experience. That's how I started my journey, thinking that being a tax, taking the enjoyment of scholarship from the taxpayers, what I could do to the society was my initial thought, and how I started out. So the first experiment I did when I started my journey as an entrepreneur was before I would electrify houses or buildings with solar energy, I should first electrify my own building that I would live, and see how much energy I would get. Would I be able to get my return on investment on the solar plant that I would be setting it up? I realized that instead of getting nearly 2 units of electricity for the investment that I had done, I was only getting 1 unit of electricity. That's when I decided I should put up a small monitoring system to this solar plant and see how much energy we would get. At that time, my very dear friend Hari joined my journey, and he and myself built this hardware software to monitor the energy generation of a small solar plant that we had set up. And we realized that it was not a pure bell shape, very pure bell shape that we were supposed to get. We were getting a curve that you are seeing in the graph, and we were able to see that the energy generation was affected because of various shadowing effect and various what do you call the nearby trees and other thing that was affecting the energy generation. That's when we realized that it's not just only about putting up a plant. You also, I mean, data was helpful in understanding what are the duration of the time that we were able to lose the energy, and how we could eventually plant improve. So it helped in two ways. One is understanding why we are not getting energy, I mean, through the data. Other thing is what is the constructional change that we have to do in the solar plant to increase the overall throughput. Yeah, I mean, while we were fascinated about our project, we were not making any revenue. So that's why we ended up showing this work to Indian Staff Science at DHR Center for Climate Change, and told them we have done something like this. They told, oh, we want something like this to see how much more energy you get from a tracking system over a static system. So we set up this system. The one on the left side is a static system, and the right side is a tracking system. Tracking system, like it tracks like a sunflower. Of course, sun doesn't move, but the tracking system would see the trajectory of the movement of sun rays, and would help in getting you maximum energy generation. So what we did was we did up this energy monitoring system to understand how much energy you get from individually. So of course, our initial system back in 2011-12 was very bulky. We also got support from National Instrument to use their software LabVIEW. And we put up this energy meter. Since I had already worked in energy meter business with GE, I would not invest on building energy meter, use off-the-shelf energy meter. And we put the software in the computer and we were able to see the energy generation. I don't know if you can observe here, the energy power generated from DC1, that is a static system, is 149, around 150 watts, and from the DC2, which is a energy generated by a tracking system, was 313, almost the double the energy generation. I mean power generation, and energy, you can see it is also more than double the energy generation. This is at 8:37 in the morning. So we realized in the morning hours, the energy generation from tracking system was very high, and so would be on the evening as well. So this was our first understanding on how you could use data science, or data, just not even science, data to analyze this kind of sustainable technologies system. So while data was extensively used in all the other systems like gaming or entertainment and all the things, now we thought we could use it for sustainability and things like that. This was our initial project that led to us seeing the value of how we could build this database data in this field. As you can see, the date also is around 12/7, around July 2012 we had done this. Yeah, coming back to the problem, I think I don't have to go extensively into it. Deva has already talked about it. So a simple question, if we just ask ourselves, how do we get energy and water, then we will start thinking about how to save it, because it's a very complicated route that we get electricity. I mean, right now in Hyderabad, but when I look at Bangalore, I know that the energy is not generating from, of course, in my lab, it is generated from the rooftop, but elsewhere it is coming from a from a thermal power plant or a hydroelectric power plant, and then goes through this long transmission and distribution, and then you would get electricity to your house. There's a substation close to your thing. So I'm sure you have more experts in this field who knows that how electricity comes to your place. So there's multiple BESCOM, the transmission distribution network and generation, all these things combinedly work together to ensure that you get electricity. And there's a lot of electricity loss that has substantially come down over the years thanks to digital intervention. So my point is saying that there's somewhere a lot of coal being burned for us to even do this conference call today. If I think about Bangalore, the water comes all the way from River Kaveri, and in Bangalore is at a very high altitude, and you know how much of electricity is required to pump this water, purify this water, when we could have just harvested this water on our rooftops and just filled our sump. I mean, considering the fact that there is rainfall. But unfortunately, that's not the that's how we get water today. We get it from almost 120 kilometers since from River Kaveri, and now there is also water from Kaveri is reached the upper ceiling of 900 million liters of water per day, and so and groundwater in Bangalore is almost running out. Now we have to get other networks of water. It is a very big tragedy that Bangalore was considered as a in one of Govinda movie, Sergeant Saleh Saral used to say it's a I'm going to Bangalore for honeymoon. But today is no way close to it. We had so many lakes, 900 lakes before I was born. And today we have handful of lakes, and we also have stories of it getting caught fire. So that means we are actually doing very unsustainable thing. Climate crisis is a result of all this emission, whether it is water, energy, waste. There are multiple aspects. So I'm just sticking to what. So this is a global estimate of. I mean, they have been able to show how the temperature of the planet has increased over a period of time. Obviously, it is proved by scientists that it is human. It's not just only because of the sunspots and all those things. There is always debate on whether it is sunspots and other things causing various other debates whether it is human. But today it is proven by scientists and accepted at a large level that it is caused by human activities. So there are various effects of climate change. I'll not talk much about it, but it is just not, people just think it is like the raising on the islands are going to drown, which is going to, but there are various other aspects. Warmer planets leads to more malaria and other diseases, and it also leads to agriculture yield, and because hydrology, I mean, there's a change in evapotranspiration, there's a change in hydrology, and because of which there's a change in rainfall pattern. There could be drought in some place, heavy rainfall, and cities like what you are living today, what was built by Ashoka to Akbar, was designed when the temperature of the planet was much lesser. So now the same place where you get where the cities were architected, designed, are not the same place where the temperature is same, and so there's a lot of larger consequence which is not talked about. I would highly recommend a talk by somebody like Mrudula Ramesh, or somebody who is an expert in climate, or Dr. Veena Srinivasan from A-Tree, to give a larger lecture on this climate change. Yeah, I would let's talk about. Yeah, I did all my education in technology. I mean, information communication technology. So I was wondering, while I could do some changes in my personal life, what can I do in terms of solutions? So I thought, since I'd worked in Celco, and I'd worked where Celco was doing energy generation from solar energy and giving it at that site itself, and I'd worked with G Energy, where there was energy there a smart grid that would distribute energy at large scale. What is how can we strike a balance? And Deva and Tanuja have extensively worked on this technology called microgrid, and but I was thinking of what I can do. This was back in 2010 when I had just left. I mean, 2011, of course, is the year I was just doing cycle rides. I was thinking, how do we give electricity and water to our people? And the year this, by doing these cycle rides, I was able to see that electricity penetration was not there everywhere, and water availability has its own consequences in various level. So I thought, why don't we build a small grid and distribute electricity and water in some way? So I just didn't want to complicate the problem. So I just thought, let us at least solve the electricity problem. So we were thinking, while you could build a small grid, the maintenance of this grid would be a challenge, because if it's not a big grid, who would maintain it? So you have to come up with a plan to even see how we would take care of. Would you have human resource to manage these kind of small grids? Because the opportunity to take care might not be enough. So, and the labor cost in places like this, how do you manage training and all those things would be very challenging. That's when we thought, why don't we put monitoring? Since I had my initial luck with that solar plant that I showed with you, I thought, I was of course I was romantic about this idea, not to deny that. I was thinking, how would you use the data to actually manage such small grids? So we came up with this IoT data science application, used the health monitoring system to understand solar plants and monitor individual points to monitor energy and water. Initially, we thought about doing it in energy, and make it smarter, put wireless sensor, and try to get this thing. So this was the idea, and I shared it with my bunch of my friends. They told Ganesh, this is very interesting, but all these things won't work in the ground. So please, it is a good to write a paper and get a good publication, but I don't think these things work. I know you come from GE and IISc and all those things, but sorry to say, I was definitely disheartened. I thought, yeah, what to do about it. My interest to do this was slightly more than getting disheartened. So I thought, if not doing on the field, let me doing it in a lab scale. A solution like this, can I at least build a solution like this at a lab scale? Yeah, I mean, we were playing too much of table tennis. I was playing too much of table tennis rather. So then I thought, let me use my table tennis to build a small microgrid on the tabletop. And that's how I thought, like, well, let's put a small microgrid on the tabletop. It would look something like this, where we put up this thermocol based thing and try to see if we can electrify this house using the same power plant that I showed in my earlier slide. It was not very attractive, so we thought, let's make it look attractive with some stickers and make it look more appealing. So like this, we put a small microgrid on the top of a table tennis thing, and we lighted it up and powered from the solar. So like this it looked. Of course, the previous one was very messy, but like this, we made a small microgrid and electrified and put up energy meters that we had used in my first project. To see how much energy is consumed by individual. Can you actually moderate this electricity generation? We wrote a software to actually monitor the energy generated by solar plant, monitor the energy consumed by individual house, and see if they consume more than a certain, say, 0.3 units of electricity, they will cut down. They will have a quota of electricity like a prepaid system or postpaid system. We have developed the software to actually manage this small grid. And that's when we actually showed it to all the people and skeptics of this work. They told, oh, you're really wrong. I think it might work and you should not give up. Sorry, I'd given you this, but I'm happy that you didn't give up. You actually started working on it. And the Divecha Center for Climate Change at the Institute of Science was willing to fund a project like this in a place where there's no access to electricity at all. So since we found a place where there is, reserve forest area, you're not supposed to increase extend electricity grid. So we identified a place called Beamgad Wildlife Sanctuary, and we thought we'll electrify this village. So this is a place where there's absolutely no access to electricity, wildlife around, no transportation. I'll show you some pictures, or no medical facility. People had to really, they were living a life which was very below the kind of life that we all live today. The kind of benefits that we have because of urbanization, they would have not even close to, I don't know, I can't really elucidate it in terms of numbers, but very, this one like. So this is the exact picture of that location. It was a beautiful place. We enjoyed trekking this location. You know, I was in my 20s and late 20s and not married. So, you know, I was living the life of how we can solve the problem of our country and highly romantic about solving with this technology. But yeah, I mean, the truth was that yes, that the location was very, while it was beautiful and all those things, they had lacked basic amenities. And this was the time when Dr. Abdul Kalam was talking about Pura, providing urban amenities to rural areas. So we are asking them, what are the amenities that you had? So before that, doing any, there'll always be an incumbent system before you come up with. The incumbent system was they were using kerosene lamp, chula, and they were lighting the thing. It causing indoor pollution as well while it was giving light. They were also able to use a battery which was charged by a truck nearby. They used to carry it for 5 kilometers, use it for a week, and again take it back and charge it for a day or two, and get it back. So they were using a very primitive. On top of that, they were using an inverter which had 30% efficiency. So that means even if they had a 100 ampere battery, even if they would only get 30% of it, like 30%. And it was not a deep discharge battery, so it only get 15 ampere hour level of energy. So they were using a very suboptimal system. So this was our understanding. One is understanding what incumbent system they had. The other is talking to people. So we talked to everybody in the village. In fact, that I had some learning of design thinking and other thing because of GE. I realized like we should not build something without talking to people or deploy anything. We talked to everybody in the village. We talked to the Mikasa, we talked to the village ladies in the village, and we talked to the children in the village. But what really got us attention was the children told that we asked them, why do you need electricity to everybody? I know it's not this one, but because we want to set up electricity, we want to understand what is their primary need for electricity. Is it for lighting or whatever? So the children told, we want to do homework and we want to become engineers, doctor and officers. And we want to be like the people in the city and be as competent as. This was when it touched our emotional chords, and we decided no matter what, at least for these kids, we will do this solar project. We were exploring various locations, but I should say more, see, you know, all selling for that matter is emotional. So we were touched by the children's intent to actually succeed in their career. So that's why we decided we'll electrify. So we went to the Gram Panchayat there, and they told, sir, I think it's all great, but we can't give you any land to set up this solar plant. Asking, then but we came here all this way, we can't do this. But you know, they say red obstacle is the path. So they themselves told that you don't have to see, why do you want to take land from forest official and all? Why don't you just ask the village people? They only give you small land. Of course, you're doing for the welfare of their life. So that's when we actually decided to talk to the villagers, and the villagers agreed immediately, saying that, oh, why don't we give, please let us know how much. And we got that. And we also had to take permission from forest official to transport goods inside forest area. So we took all the permission, and the Divecha Center for Climate Change, whom I showed you the earlier project of tracking system and static system, they had already seen our technical capabilities through the project, so they were willing to fund this project, right? So what I'm also trying to tell is an aspiring entrepreneur out there. There's no exact path, but there is a path when you actually follow certain thing, and we were, I don't know whether we did it right or not, but this is our route. So maybe hopefully it will help. So my intent is to some of those data scientists and engineers who want to take up entrepreneurship while using advanced technologies. So these are some small things that can actually matter when you are actually on the ground. So like this, we started electrifying that village. So the thing is, initially we wanted to put underground pipes and put electric cables, but they said that no. I mean, we want electricity where there is electric pole. That's when it is real electricity. I mean, the exposure level to the villages was limited. That's why they were not able to understand that it is not the electric pole that is important. It's just a means. So, but we realized that it is important to talk to them in their understanding and their language. So we decided to put electric pole there. And they'd also said, we had during our interview with the people, the ladies in the village had told that we can't go to urinals in the night because there is no light in the night, and it's very lot of challenges in that respect. So putting electric pole also meant we would put street lights there. So that way we were also able to accommodate street lights on this thing. So like this, we put up the solar plant there, and we were able to, we designed the solar plant based on the funds and based on the user interview, understanding what their key needs of electricity were. And we were able to deploy a pretty good 2 kilowatt system, 2 kilo WP system in this location. And we put the same energy meter that we had put in our demo setup in our lab. So that's why it's very important that I had learned this from my time in GE, that if you solve a problem by design, you solve it at $1. If you solve the problem at laboratory, you solve it at $10. If you end up solving the same problem in the field, it will cost you $100. After deployment, your reputation is at cost. So we did so much of work in the laboratory, though we didn't solve everything at the design. We were able to solve most of those in the lab because this was a deep jungle. If anything we had forgotten or not done in our lab, we had to go all the way some 50-60 kilometers and trek along and go. So that way we were able to do a serious good testing in the lab to make sure the system works first time. And this was obsession in GE to do right the first time. And that value system, I took it forward when I took up this job and this entrepreneurship. So we, of course, we were funded by Divecha Center for Climate Change. So we had to put weather station. Initially, we had put this weather station at this height. Of course, we increased the height. We were not getting right data because the height of that pole was not obstructing certain data points. So, but the best part was we used children and the villages there to set up all these things. So we are a small company. We didn't have enough people to get there and do all these things, and we utilized the local resource. Like this, we were able to do exact wiring like we did in our small plant, and the electricity monitoring, everything was done using single board computer, and we were able to take data. We had not done wireless, we had done wired, used Modbus communication, and we configured. Since everything was done in the laboratory, we just had to deploy the thing. There are other challenges which we were able to take care by help of the villagers and nothing. So this was our, so that's not a weather station, solar plant, and we were able to put the data monitoring because this project was funded by the Divecha Center for Climate Change to get the data of the system and understand how do we scale future microgrids, like build a policy recommendation on microgrids and come with a advisory to even the government to ensure how we can electrify villages. So this project was more of a understanding all the challenges and use data to come up with right sizing of microgrids, understand what is the weather data, how will weather data have an impact on your energy generation, temperature, incoming solar radiation, bunch of these parameters. So we built a smart monitoring system, and we were able to monitor the energy generated by the solar plant, weather data, energy consumed by individual house, battery charging data, solar charging data. I mean, solar. So all this thing helped in, yeah, this girl getting electricity. She had never gone outside that village. Ladies generally you would not go outside the thing, but of course the men would do masonry work and all in Panjim and other region. So first time in her life she was able to see the electricity that they always wanted. And of course this year the passing percentage in 10th standard increased almost by 70%. And not that we did the homework or they did all the hard work, but you can see how electricity has an important role to play in something as completely different like education, right? And it has its own thing in health and other things, right? So we were able to, I mean, not just that, this girl was able to go to college after years later. Like this, of course, was done in 2013-14 time. She went to college, and I've now lost track of the thing, but I was told that this one. So, and not just that, they got television. So it's not just about watching. They were watching Chitrahar, Rangoli, and all, but they were also watching, EduSat and other program. So that way, a level playing field was set up for them. I mean, like they were getting urban amenities, like what Dr. Abdul Kalam was talking about. So we were very happy to see this, and they were able to use electricity even to watch television. And it is very interesting that they were mobile network, but no charging facility to charge their phones. So they were able to use telecommunication networks to make calls with their loved ones. So now coming to the data science, I know I'm talking more about all the other aspects. So you can see on a day when there was very good sunlight, on a day when you get full sunlight, they would not even they would sleep without switching off the lights. They would use the entire time light. But on the day when there is not enough sunlight, the battery would also have days of autonomy for certain duration. They realize that they have to consciously use electricity. If not, some days they will not get electricity at all. They will not be able to watch their favorite television program, not able to do homework, not able to get the benefits of electricity. So that's how we also understood that the days of autonomy has to be increased, because some of the days that there'll be good sunlight and then you can charge it for a longer days. So that's why we were able to. So we of course wrote a paper that I'll be happy to share. IEEE Smart Grid Conference in uh, Miami. We presented this work, and this also went on to various other. I'll share the paper with Tanuja. I can share it. So we were able to see the day when the sunlight was lowest, the energy consumption was highest. So it's natural, right? When the darkness prevails. So that's how we have to come up with the right sizing of these solar plants and the battery, and depending on the geographic incoming solar radiation and various other pattern, you have to do the right sizing of solar plants and build such microgrids, right? And this was our understanding. And yeah, I mean, we had our own challenges in this. So I know I might be running really late, so I'll quickly finish. I know I'm really sorry on this one. I'll quickly run through. So we realized that, see, I mean, while there was a financially they were not able to pay for this. So while this was good to policy recommendation and others, as a projects we had done for larger intent, we were trying to see how we can monetize on this technology for solving problems in other areas, and we as a company can grow. We tried to do this in apartment and other, and we developed this thing. We while we were promoting this energy, we realized the traction came in water. So we came up with energy and water manager as a product, since we had seen this thing. So we did the same thing for an apartment or a factory like thing and show the demo. We had seen the success of building a prototype to show a success of a idea or a technology. So we want to utilize it again. We did this monitoring of water and showed how there's almost water getting wasted and water being mismanaged because there's no data for water. This got attention of one of the very interesting, I mean, company. There is Titan Jewelry Division. They actually saw this and in an event and told Ganesh, we want this thing. Nobody does this. Can you help us reduce? We have not increased our production significantly, but our water is getting wasted. I mean, we don't know where it is happening because we don't measure. So can you help us deploy the solution? So from there, we started seeing how we can use data to manage water. So how is the incoming? So back in 2016, we started realizing there's also Niti Aayog report that came later that 18 cities in India would run out of water because they are so dependent on groundwater. So that's when we started utilizing data for solving the water. This Titan Jewelry Division. So what we did was, I think there's some. Okay, so what we did was there's some slide missed. Okay, so they were not able to understand where there's leakage, wastage, excessive usage of water. They were over leakage happening, and they were not able to figure out. So what we did was we digitized their water infrastructure by putting existing water flow meters in the market, and we were able to put all the part through solar and came up with a solution where they would be able to see the wastage, leakage, and identify inefficiencies in the water network, right? So we were able to put sensors across, and we were able to deploy the sensor and see where there is. So initially, it was all about data monitoring. Then we started visualization, and then we were able to use algorithms to find out leakage, wastage, and bring this entire whole project into understand the entire balance chart of their thing. And the visualization also helped in understanding exactly where there is water getting wasted. So before that, they were running, they used to have staff that used to just run around doing visual inspection, seeing things where there is leakage, where there's wastage, underground pipes, so they would never come to know. So using this, they were able to use these algorithms, also able to help in understanding where there is, using pattern recognition of water data. We were able to say whether it's a consumption or wastage. So through this, we were able to even generate reports for their internal audit and external audit. The audit would report would have them get prescriptive alerts on what to be taken care. And we used to have quarterly consulting to help them. So what we did for Titan, we realized this is the problem that we want to solve as a company. So we had to take a pivot in our business model to what we came with energy problem. We started solving for the water. So today we have more than 50 plus clients, saved more than 1 billion liters of water so far. And our goal is to, just like what we solved for Titan Jewelry Division, we want to solve for all the industries. Because when there is a competition for water from a resident, from an agriculture and industries are in big risk, because their water will always be prioritized for residential and agriculture. So we came with this how data driven approach, using de-risking industries on water crisis. We are now trying to use not just of course terrestrial data from IoT sensor. We are looking hopefully use drone and satellite imagery also to solve this problem of water for industries. Very thankful to Cisco Launchpad for us giving us, when we had just one customer, they helped us to do the product market fit, and that's how I met Deva, and of course Tanuja helped us from the Microsoft for Startups, from Project Amplify, and we are also supported by Berkeley, NATSCOM, and Deshpande Startups to for whatever we are today because of all the support that we have got. And today we have an end-to-end water intelligence platform to save water up to 30%. This is what we do as company Flux in our product acquisition. And what we do is we monitor water infrastructure, flow level, pressure, energy consumed by water infrastructure, water quality, and use our patent pending IoT hardware that helps in sending the data to the cloud. Today we use Azure to actually send the data to the cloud and help in we also have integrated our solution with various Cisco's IR829 platform and various others. So we have been working with various platform to expand our thing. We've been lucky enough to get some national international award for our work. With this, thank you so much. I'm sorry I took more time for my presentation. I'm also founder of another organization called the Sustainability Mafia. We feel all the non-sustainability guys are a mafia, so we need a sustainability. And AirPro was a company which we built, which got acquired by a San Francisco-based company. And we have Wednesdays for Water every Wednesday, where we share the knowledge of water with. We have people from all back coming and sharing, including people who are policymaker, Padma Awards winner, and others. And yeah, this is I'll happy to connect with anybody. We are growing our business, want to get support from minds like you all on how we can do our work better. So thank you so much again for the opportunity.
Thank you, Ganesh, for such a wonderful talk. I personally appreciate you for your thought about giving back to the society and reaching out the deprived section of the society, and helping them to get educated through the solar electricity and all those things. I'm sure everybody would have got inspired by your work here to give back to the society. That was a really awesome presentation. Thank you so much. Anyone has
Thank you for the kind words. I'm sorry if I didn't do much justice on the machine learning and AI part.
I think we can have one more session on that later, but definitely we would love to have you back here for from IEEE. Anyone has any queries you would like to ask anything to Ganesh? Okay, I don't see any questions in the chat. Anyone?
I have a question.
Please.
Yeah, this is Deva. Ganesh, thanks for your extraordinary generosity as always. So what I wanted to ask is that, in your experience, do you see, people prioritizing the climate impact over balance sheet? Or is that changing or not changing?
The timing of this question couldn't be any better. Just yesterday, Patagonia, this one founder gave off all his wealth for the thing, multi-billionaire. I think is a $4 billion. He actually, I mean,
I read that, from your experience, Ganesh. I mean, I know that. I know, like, Bill Gates is investing and all that stuff. But from your experience, when you're interacting with the customers, do they say, okay, this is more important? Conserving water is more important than another 0.1% of profit margin. Is that happening? So,
So
please.
there is no yes or no answer, as you know, Deva. But what I realize is climate action and sustainability is also a business imperative today. If I'm saving water, that is a saving on their bottom line. No, if they're able to give if they are able to use clean energy, that's a today solar energy costs cheaper than coal. And another thing is today big industries are worried about how climate change would impact their indirectly affect their balance sheet. It is said that if floods like this happen, if the people will just give the this one to the top leader saying that, oh, we were not able to meet our financial target, sales target, because there was flood, there was that calamity, that this. So they have started realizing it is not just only about doing the good, it is directly affecting. If you consider BlackRock, they have asset which is more than $10 billion thing, right? $10 trillion asset management, like in Procter and Gamble, various other things. So they have started seeing that this is affecting their own investment, where it is directly affecting them. It should have been almost 20, 30 years back, the awakening should have happened. But today the awakening has reached a threshold that they realize it will affect their own larger interest. So my thing is today they are seeing it from a strategic point of view on how it is going to be helpful. But there are definitely a lot of people I have met who have their heart in the exactly right place where it should be. I mean, in the place where it should be, and looking at it. Just yesterday, I met Mr. Jamshed Godrej, and I realized they had come up with all the sustainability initiative even before many of this mandate. And so today I'm actually at the Greenco Summit where there are other leaders talking about it. So it has reached a inflection point or a tipping point for leaders to start realizing this is just not going to sustain this way if we neglect it like we have neglected it for like decades together.
Yeah, thank you, Ganesh. It's great that you are holding the flag. So, thank you.
No, I'm just doing a very nano bit or very small part. This like a small squirrel that Rama was trying to help build Rama
with a name
Setu.
like that, it's an auspicious start. So thank you.
Thank you.
Thank you. Anyone is having any other question? Okay, I don't see any further questions. So thank you once again. So we are at the reached the end of this particular symposium on AI for social good and sustainability living. Thank you, everyone. Especially my special thanks to all the great speakers over here and all the great audience. Also, you have been very interactive and asking the questions, and very patient listeners as well. And I also would like to thank Prashant Mishra, who is a chair for Computer Society, IEEE Bangalore section. And I would like to thank Amit and Tanuja, who have really put in great efforts in bringing in the speakers for today's symposium. Thank you, everyone. Thank you once again. Have a great day.
Bye.
Yeah, may I just come in, Amit? Maybe have a photograph with all the attendees at this point and the speakers, whoever are present. Just everybody could turn on the cameras and we can take one screenshot.
Cameras on.
Okay. Others, if you could also switch on your cameras, if you are comfortable, then it'll be great. Okay, fine. Sure, Amit, one screenshot of this would really be nice.
Yeah, I took one. Okay, I got Nipun now. Nipun just came online. Just a second. Okay, I got it. Thank you.
Thank you.
Thank you, everyone.
Thank you.
Thank you. Bye.
Bye. Thank you.